Hello there and welcome back to the Sleep Science. Tonight you find yourself standing inside a dimly glowing laboratory, the kind where the air hums with static and the walls are lined with pipes wrapped in frost. You can almost hear the soft sigh of helium vapour whispering past your ears. Before your eyes sits a strange chandelier of gold and wires, a quantum computer's heart. It looks more like steampunk jewellery than the future of technology. But make no mistake, this is the dawn of quantum reality. The hum you hear isn't just machinery, it's the sound of physics itself being rewritten. You probably won't survive this. Well, not in your current understanding of computers at least. After tonight, the world of bits and bytes may feel quaint, like rotary phones or floppy disks. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, drop your location and your local time in the comments. I want to know where in the world you're tuning in from as we step through the veil of classical logic together. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You reach out, fingers hovering just above the gold-plated tendrils of the quantum processor. The air feels alive. Each wire is a highway for microwave pulses racing to control qubits, quantum bits, that live in states your mind can barely imagine. Unlike the computers you know, this one doesn't flip switches between on and off. It drifts somewhere in between, both states at once, like a cat you both fed and didn't feed, Schrödinger style. If you've ever stared at an old hard drive and thought it was complicated, you'd laugh now. This machine doesn't process information in linear lines of logic, it folds it. Inside those superconducting loops, electrons surf waves of probability, existing everywhere and nowhere. And as eerie as that sounds, it's real. The first glimmers of this reality started long before tonight's lab visit, way back in the 1980s, when physicists like Richard Feynman and David Deutsch began asking, what if we built a computer that obeyed the universe's actual rules instead of the simplified ones? Feynman, famously mischievous, once quipped that, nature isn't classical, damn it. You can almost imagine him saying it now, chalk dust on his sleeve, as he watched early quantum theories grow from thought experiments into prototypes. Historians still argue whether he truly foresaw the technological storm we're now living in, or if he just tossed out another one of his playful challenges to the future. The quirky truth: the very first quantum computation wasn't performed in a fancy superconducting fridge or $1 million facility. It was demonstrated in the late 1990s using molecules suspended in a simple liquid, manipulated by nuclear magnetic resonance, the same principle as MRI scanners. Basically, a quantum computer once lived inside a test tube. The entire experiment could have fit in your backpack, though good luck explaining that to airport security. As you walk deeper into the lab, your shoes echo against polished concrete. Rows of control racks blink in coordinated rhythm, each tiny LED reflecting the vast data ballet happening inside that gleaming chandelier. Engineers whisper around you, their voices muffled by layers of cryogenic shielding. These people are the keepers of the world's coldest secrets, literally. Some of them spend more time talking to dilution refrigerators than to other humans. There's a subtle irony here. We built machines capable of near-magical parallel computation, yet they rely on ancient human patience. The system must cool to less than 0.015 Kelvin, colder than deep space, before even one qubit will behave. One researcher jokes that working with qubits is like training cats. You can't force them. You can only create conditions where they choose to cooperate. You lean closer, the hum steadies. What's truly mind-bending is that every flicker of light from those control panels represents a physical experiment that reshapes reality in real time. Each measurement collapses a wave of probability into a single definite outcome. Before that moment, the computer doesn't just not know the answer, it holds all possible answers at once. That's the essence of why tonight feels historic. Quantum computers have been teased, mocked, doubted, and hyped for decades. Yet the room you're in, real hardware, real output, marks the end of that long theoretical adolescence. You're witnessing a moment physicists used to treat like science fiction finally crossing into engineering. A soft chuckle escapes you as you recall a fringe tidbit from the early quantum days. One of the first practical proposals for quantum communication came not from a physicist but from a magician-turned-mathematician named Charles Bennett, who wanted to teleport quantum states, and he actually helped invent quantum teleportation. Not beam me up teleportation, of course, but the kind where information leaps between entangled particles faster than your coffee cools. Even now, historians still argue whether that moment, Bennett's paper in 1993, was when the line between quantum theory and quantum engineering truly blurred. Maybe that's the real beginning of tonight's story. The instant a concept so weird it made Einstein roll his eyes became something you could measure, tweak, and one day market. As you stand surrounded by cold brilliance, a quiet realization settles in. This isn't the future. This is now. The quantum era isn't waiting for us to catch up. It's already computing quietly in the background, solving optimization puzzles, simulating molecules, maybe even helping design better versions of itself. You breathe out, watching the air curl into mist before dissipating into the sterile chill. Somewhere behind you, a scientist presses a button and the chandelier flares for a moment, shimmering like frozen lightning. It's not a spectacle, it's a signal. The line between theory and reality has officially been crossed, and you're standing on it. You can still feel the hum of that machine in your bones as you step away, trying to wrap your sleepy mind around what it all means. Somewhere deep inside that shimmering chandelier of gold, the future is whispering, but to understand it, you have to take a few steps backward. You can't appreciate a quantum revolution without remembering the quiet tyranny of bits, those loyal, predictable soldiers of classical computing. For most of modern history, information has marched to a binary rhythm. 1 or 0, on or off, yes or no. Every song you've streamed, every cat meme you've sent, every spreadsheet you've pretended to understand, those were all just long strings of binary decisions. A bit is basically the world's most decisive particle. It picks a side and stays there. But quantum mechanics? Oh, it hates commitment. You picture a qubit, short for quantum bit, like a coin spinning in slow motion. A classical bit is heads or tails. A qubit, though, is the coin mid-spin, embodying both outcomes until you stop it. In that blur of motion lies its power. Each qubit can store not one, but many possibilities at once. And when you start stringing them together, their combined possibilities multiply exponentially. A handful of qubits can represent more states than there are atoms in your fingernail. No wonder physicists sound sleep-deprived all the time. You glance around the lab again, noting the control screens where engineers monitor these ethereal coins. A technician explains how qubits can be made in several ways. Trapped ions floating in electric fields, superconducting loops where currents circle endlessly, even photons zipping through crystal lattices. The sheer diversity of approaches feels almost rebellious, as if the field can't decide on one flavor of impossibility. There's a quirky historical fact about this indecision too. Back in the 1930s, before the term quantum computer existed, a German physicist named Erwin Schrödinger, yes, the cat guy, actually proposed that electrons themselves could be treated as waves of probability. That idea sat in dusty journals for decades before anyone realized it could form the foundation of a new kind of computation. Historians still argue whether Schrödinger would have approved of his equations being used to build machines rather than metaphors. He was famously annoyed that his wave theory turned into a cat meme before memes were even a thing. You can't help but smirk. If only Schrödinger had known he'd be trending on TikTok. Bits, on the other hand, had a much tidier history. In 1948, Claude Shannon formalized information theory, giving us the beautiful, rigid logic that underpins everything digital. He treated data as measurable uncertainty, entropy with a side of math. For half a century, we were content with that binary empire. It powered our phones, our satellites, even the simulation you might be living in right now. Kidding. Probably. But nature never agreed to those limits. Electrons tunnel through walls. Photons interfere with themselves. The universe seems to prefer ambiguity. And so, sometime in the late 20th century, human engineers decided to make peace with that ambiguity rather than fighting it. Thus, the qubit was born, a rebel against determinism. You reach out again, imagining yourself holding a qubit in your palm. You can't, of course. The moment you measure it, it picks a state, collapsing all that shimmering possibility into one result. It's like trying to photograph a dream. The act of looking changes it. That's the trickiest part of quantum computing. Observation itself can destroy the magic. To help you visualize, one of the researchers nearby gestures at a small screen showing a colourful sphere spinning lazily. That's the block sphere, the map of a qubit's entire life. At the North Pole, 0, at the South Pole, 1, everywhere else, infinite shades of maybe. Each qubit dances across that sphere, guided by microwave pulses, balancing probabilities with the grace of a ballerina who refuses to pick a favourite move. It's beautiful, but it's also maddening. The fragile nature of quantum states means any stray vibration, magnetic field, or cosmic sneeze can ruin the computation. You think about your laptop overheating when you open too many tabs. Imagine if breathing near it could crash the system. Yet here, in this cryogenic chamber, dozens of these finicky particles coexist, shimmering in disciplined chaos. There's a lovely bit of fringe trivia floating through your mind. The first qubit-based chess program was once written just to see if it could refuse to pick a move until observed. It technically played a game against itself that lasted an infinite moment, until a grad student, impatient, measured it and ended the match instantly. Quantum checkmate. You smile at the absurdity, but also at the wonder. This in-between state, this refusal to commit, is exactly what gives quantum computers their edge. While classical processors crunch through options one at a time, qubits consider all paths simultaneously. When properly orchestrated, that means a quantum computer could, in theory, solve problems that would take classical machines longer than the age of the universe. Of course, in theory is the key phrase here. Historians still argue whether the leap from bit to qubit represents a true technological revolution, or just a new mathematical language to describe old physics. Some claim it's overhyped, others whisper that it's the dawn of post-human intelligence. The truth, as always, probably exists somewhere in superposition between the two. As you drift closer to one of the control racks, the hum deepens. The scientist beside you adjusts a dial, sending pulses into the qubit chamber, and you realize something both comforting and strange. Despite all the jargon and quantum poetry, this is still engineering. Wires, chips, timing circuits, each one grounded in classical reality. The extraordinary rests upon the ordinary, and yet, it feels personal. Somewhere inside you recognize a mirror of your own uncertainty, the feeling of being both one thing and another, the countless versions of yourself hovering in potential until life collapses you into one path. Maybe quantum computing isn't just a leap in technology, maybe it's an echo of consciousness itself. The technician gives you a thumbs up and you nod back, pretending you understand the math. You don't, not really, but that's okay. Tonight isn't about decoding every equation, it's about feeling the shift. The world once ran on certainty, and now it runs on possibility. Somewhere, deep in the chilled belly of this lab, the line between on and off has blurred forever. You linger in that quiet hum of possibility, and it's almost hypnotic. The gentle rhythm of fans, the low rumble of cryogenic pumps, and beneath it all, something you can't quite name. A faint vibration in the air, like the universe is whispering secrets to itself. That's superposition in action. You don't see it, but you feel it. The universe refusing to make up its mind, and somehow, you're complicit in its indecision. Superposition is the trickster heart of quantum mechanics. You've already met the qubit, that indecisive coin mid-spin. But superposition is what gives that spin meaning. It's the reason the coin can hover in a blur of both heads and tails without choosing. In a classical world, that makes no sense. You'd call it cheating. But in the quantum world, it's just business as usual. Imagine standing in front of two doors. In the everyday universe, you pick one. You walk through, end of story. But in the quantum version, you split into two versions of yourself. One walking through the left door, the other through the right. And both exist until something, or someone, forces the universe to decide which you really chose. It's both poetic and a little terrifying. You might be thinking, alright, that sounds like science fiction. And you'd be right. To everyone before 1926 it was. That was the year Austrian physicist Erwin Schrödinger formalized the equation that governed superposition, the one that would make him famous for torturing a hypothetical cat. Historians still argue whether Schrödinger created that cat to mock quantum logic or to illuminate it. Either way, the cat has outlived him by memes alone. You picture it now curled up inside a box purring, or not purring, depending on who's looking. The cat is a metaphor for all qubits in existence, suspended between outcomes, waiting for observation to collapse the wave of probability. You chuckle softly. Somewhere out there, millions of people use the term Schrödinger's cat to describe their love lives, job prospects, or online orders. Quantum mechanics, in its own way, has become the language of everyday uncertainty. In the chilled glow of the lab, a researcher shows you a small graph on her monitor, a pattern of peaks and dips called interference fringes. That, she says, is proof of superposition. Each peak is a place where probability waves overlap and reinforce each other. Each dip is where they cancel out. The qubit, while in superposition, isn't just undecided, it's calculating across possibilities simultaneously, letting probability itself do the math. Here's the mainstream historical fact that still astonishes people. The very first direct demonstration of quantum superposition wasn't in a fancy quantum computer at all. It was Thomas Young's double-slit experiment way back in 1801. 2 narrow slits, 1 beam of light, and an interference pattern that shouldn't exist unless light behaved as both a wave and a particle. Over 2 centuries later, scientists have repeated versions of that test with electrons, molecules, even entire clusters of atoms. Every time, nature shrugs and says, "Yes, I can be in 2 places at once. Why can't you?" A fringe tidbit for you. In 2010, researchers in Vienna performed a version of the experiment with organic molecules containing over 800 atoms. They were, quite literally, putting a small speck of matter into a superposition of being here and there simultaneously. Somewhere Schrödinger's cat is rolling its quantum eyes. Still, historians argue whether superposition is real or simply a clever mathematical tool, a description of ignorance rather than physical truth. Einstein hated the idea that particles could exist in multiple states until observed. He called it incomplete. But experiment after experiment keeps saying otherwise. Every time scientists try to catch quantum mechanics breaking its own rules, the rules hold steady. It's almost as if the universe likes being indecisive. You lean against a metal railing, watching a string of data pulse across the monitors. Superposition in a quantum computer isn't philosophical, it's practical. Each qubit's ability to hold multiple values simultaneously allows the system to test countless combinations at once. Imagine solving a maze not by walking it, but by splitting yourself into infinite copies that explore all paths at the same time. When you measure the result, only the winning version of you remains. The rest simply never were. There's a joke floating around in the quantum community. A quantum programmer walks into a bar, orders a drink, and leaves. Both outcomes happen, until the bartender checks the security footage. That's the energy here, half serious, half absurd. You can't help but admire the audacity of scientists who built entire machines on the premise that reality is undecided. But as the researcher explains how qubits enter and maintain superposition, you realize how fragile that balancing act really is. Any interaction with the environment, stray heat, vibration, radiation, collapses the state. It's like trying to balance a soap bubble on a gust of wind. To preserve it, engineers isolate qubits inside dilution refrigerators, where temperatures plunge to near absolute zero. The cold isn't just for show. It minimizes energy fluctuations, keeping the quantum dance alive for a few precious microseconds. It's long enough for the qubits to hum their collective equation before decoherence sets in and everything tumbles back into classical certainty. The researcher glances at her monitor and murmurs something about coherence time. You ask how long their system can maintain superposition, and she grins. On a good day, about 150 microseconds. You nod thoughtfully, pretending that sounds impressive, but it is. Those 150 microseconds represent a triumph of physics over chaos, a moment where the universe itself cooperates with human ambition. You take another slow breath, the air still sharp and cold. Somewhere in that fraction of a second, while qubits hang between 0 and 1, a machine has performed computations impossible for any classical computer to replicate in the lifetime of the cosmos. That's the miracle of superposition. Power hidden in uncertainty. You can't help but draw the parallel to your own indecision, the way you hover between choices, futures, and moods. Maybe being in 2 states at once isn't a flaw, but a feature. Maybe the universe has always been teaching you that the in-between is where the magic happens. A soft laugh from across the room pulls you back. One of the engineers is holding up a sticky note that says, "Don't collapse the wave function," taped above a big red emergency stop button. You grin. In a lab built on quantum uncertainty, even humor is a survival mechanism. You leave the workstation, the hum of the fridge following you like a low note in a song. Superposition isn't just a concept now, it's a feeling, a vibration, a living pulse that fills the room. You realize that every flicker of light, every whisper of data, every shimmering qubit is the universe balancing on the edge of a decision. And tonight, for a brief, glittering moment, you're balanced there too. You're still thinking about that sticky note, "Don't collapse the wave function," when a voice behind you chuckles and says, "Yeah, we should probably put one of those on the universe." You turn to find another researcher standing near a tangle of fibre optics, holding a cup of something steaming. "Entanglement lab," she says with a smile. "Want to see something spooky?" You follow her past the humming cryostats into a darker corner of the lab. There's less gold here, more glass and light. Lasers cut thin lines through the air, scattering specks of dust that float like galaxies. You half expect the soundtrack from a sci-fi movie to start playing. This is where Einstein's least favourite part of physics comes to life, the so-called spooky action at a distance. Entanglement is what happens when two quantum particles, say photons, become linked in such a way that their states are forever correlated. Measure one, and you instantly know the state of the other, no matter how far apart they are. It's as if the universe handed out matching friendship bracelets at the subatomic level. "Pick a colour," the researcher says, adjusting a dial. You point at a glowing blue photon path. "All right," she says, "that one's partner is over there, 60 feet away." She taps a monitor and both light beams flicker in synchrony, as though sharing a private joke. It's subtle, almost imperceptible, but undeniable. It feels impossible. You've spent your whole life trusting that information takes time to travel, that distance matters. Yet here you are, watching reality itself ignore its own speed limit. Einstein hated this idea so much he tried to prove it wrong, calling it a spookhaft Fernwirkung, spooky action at a distance. Historians still argue whether his disdain was philosophical or just stubborn pride. He believed in a local, predictable universe, one that wouldn't cheat by letting two particles whisper faster than light. But the universe apparently loves loopholes. A mainstream historical fact drops into your mind like a stone in still water. In 2015, scientists finally closed every possible loophole in an entanglement experiment. Using photons and detectors in separate rooms, they proved beyond statistical doubt that entanglement is real. Not a trick of hidden variables, not experimental error, just the universe doing something weirdly intimate. The researcher beside you beams. "We're basically making particles that gossip instantaneously," she says. "We call that quantum communication." You raise an eyebrow. "So this is how the quantum internet starts?" "Exactly," she replies, and gestures to the web of optical cables. This setup can share an encryption key that can't be hacked, because the moment anyone tries to spy on it, the entanglement collapses. Nature tells on you instantly. You grin, a self-reporting internet. Somewhere, hackers are crying softly. There's a quirky tidbit she shares too. Apparently in the 1970s, long before quantum communication sounded remotely practical, a physicist named John Clauser conducted one of the earliest entanglement tests using a laser borrowed from a friend's garage workshop. The entire apparatus was held together by duct tape, yet it changed physics forever. It's a perfect reminder that the line between genius and tinkering with junk often looks very thin in hindsight. She shows you a live readout, tiny spikes on a graph representing entangled photon detections. Each spike is a whisper across the void, proof that information doesn't just travel, sometimes it's shared instantaneously. It's like the particles are two halves of one thought, finishing each other's sentences even when separated by kilometers. And as wild as it sounds, that principle isn't confined to labs anymore. Satellites launched by China's Mishus project have already demonstrated long-distance quantum entanglement between space and ground. That means, in theory, entire continents could one day share data secured by the universe's own laws of physics. Historians still argue whether this moment, those first successful satellite entanglement tests in 2017, was when humanity truly entered the quantum communications era. Some say yes, others claim it'll only count when those links become everyday infrastructure, humming invisibly between your phone and the cloud. Either way, the door's open. The researcher picks up her cup again, now just lukewarm, and says quietly, "You know, when I was a kid, I used to imagine that everything was secretly connected. Turns out I wasn't wrong, just early. You let that sink in. It's oddly comforting, isn't it? For all our talk of fragmentation, separation, and digital noise, the universe itself might be the most cooperative network imaginable. Beneath all the chaos, everything is connected, literally. You watch her recalibrate the photon source. 2 tiny beams emerge, intertwine, and separate again, perfectly entangled. Somewhere far away, their twins respond in sync. It's not telepathy, it's not magic, it's the universe running its own version of instant messaging. There's a funny lab poster nearby. Someone's drawn Einstein holding a tin can phone yelling, "Stop being spooky!" The caption underneath reads, "Too late." You smile, thinking how many of these experiments started as impossible dreams. Entanglement once sounded like mysticism, yet now it's a working tool, used for quantum key distribution, teleportation of quantum states, even synchronization of atomic clocks to femtosecond precision. A gentle buzz ripples through the lab as another pair of detectors click in unison. You can almost hear it, the rhythm of a hidden order threading the cosmos together. It's beautiful, in a slightly unnerving way. You take one last look at the photon paths before stepping back. Each pulse of light represents a promise, a future internet unhackable by brute force, a computing world where communication itself is quantum native. But beneath the technology, something deeper hums, proof that separation is an illusion. You close your eyes for a moment, letting the thought settle. Somewhere, 2 particles trill in synchrony, sharing a secret they'll never tell. You exhale, smiling to yourself. Einstein called it spooky, you call it serene. And as you walk back toward the glowing gold of the main chamber, the lab lights flicker just slightly, as if the universe winked at you, both here and somewhere impossibly far away. You push open a heavy insulated door and step into what feels less like a laboratory, and more like a cathedral built to worship cold. The air changes instantly, a crisp, metallic chill that bites the inside of your nose. Every sound is dampened, every movement deliberate. This is the domain of cryogenics, the quiet, frozen core of the quantum world. A technician gestures for you to stay behind a yellow line as you take in the towering machine before you. It looks like an upside-down wedding cake made of copper, gold, and silver, with layer after layer of coiled wiring descending into an open cylinder. It's not for decoration. That shining structure is a dilution refrigerator, an engineering miracle that can reach temperatures within a hair of absolute zero. You stare at the gleaming structure and murmur, "It's beautiful." The technician nods, a faint smile visible through her frosty breath. "We call them cryogenic cathedrals," she says. "It's where the qubits pray for stability." It's hard not to believe her. Everything here hums with reverence. The wires hang like organ pipes, each carrying microwave signals that control the qubits nestled deep inside the frozen heart of the system. You can almost hear it breathing, the slow pulse of helium gas circulating through an intricate maze of cooling stages, each one colder than the last. A mainstream historical fact drifts into your mind. The first dilution refrigerator capable of reaching millikelvin temperatures was developed in the 1950s. It was originally designed not for computing, but for studying the weird behavior of matter near absolute zero, where atoms practically stop moving and quantum effects crawl out from hiding. Who could have guessed that decades later, those same techniques would power the most advanced computers humanity has ever attempted? You glance at the machine again. Inside, tiny superconducting loops form the qubits themselves, each one a miniature world of possibilities. To keep them functioning, engineers must isolate them from the chaos of reality. No heat, no vibration, no electromagnetic interference, not even a curious human breath. It's the technological equivalent of meditating on the edge of nothingness. The technician leads you closer to the control console. Every qubit needs quiet, she explains. Even a single photon of stray heat can throw off an entire computation. She points to a graph displaying temperature readouts from different layers of the fridge. The lowest stage reads 0.012 Kelvin, colder than outer space. You instinctively wrap your arms around yourself, though you're standing meters away. There's a fringe tidbit she shares with a chuckle. In one of IBM's early experiments, a faint vibration from a nearby elevator caused decoherence in their qubits. The team ended up running experiments only at night when no one used the building. The researchers started jokingly calling themselves the Midnight Monks of Quantum. You grin. So this is basically the monastic order of low temperatures. She laughs softly. Pretty much. We trade vows of silence for vacuum seals. The hum of the cryostat deepens as a new batch of helium condenses. You watch as mist curls around the base, the air shimmering with cold. Somewhere inside that metallic labyrinth, qubits float between existence and oblivion, their quantum states fragile as soap bubbles. The sheer effort it takes to protect them feels almost poetic, like building an entire palace just so a single snowflake won't melt. Historians still argue whether this obsession with extreme cold will always be necessary. Some researchers believe future quantum machines might operate at room temperature using exotic materials, diamond defects, photonic chips, or even topological qubits that laugh in the face of heat. Others think that's wishful thinking, that quantum computing and cryogenics will forever be dance partners. For now, though, cold is king. You watch a technician type commands into a console. A gentle tone fills the room, and the temperature readout begins to stabilize. The air feels alive, charged with the collective focus of everyone here. Even the smallest adjustment could mean the difference between chaos and computation. Ever wonder what happens if it warms up, you ask? She smirks. We call that a very expensive sauna. You laugh, though the idea of a qubit meltdown makes you wince. The truth is, keeping something this cold takes tremendous energy. It's a strange paradox, burning megawatts of electricity just to simulate silence and stillness. Yet that's the cost of precision, of bending the universe to our will. As you walk around the edge of the cryostat, you notice small amulets and stickers decorating the equipment. Tiny acts of rebellion in a temple of science. One reads, "Freeze or die trying." Another has a cartoon penguin holding a thermometer. It seems even at the frontiers of quantum mechanics, scientists can't resist a good meme. The technician points out a cluster of tubes leading to a separate chamber. That's where the helium-3 and helium-4 mix, she explains. Their quantum properties let us reach these crazy low temperatures. It's all about making the atoms forget how to jiggle. You peer into a window where frost has formed on the metal frame, shimmering under the lab lights like a constellation. You find yourself thinking that maybe this is what progress looks like. Not loud explosions or flashing screens, but silence, precision, and cold so deep it erases noise itself. There's a whisper of air as another door seals shut behind you. The sound seems amplified, like the world outside is miles away. In a sense, it is. Time moves differently here. Each cooling cycle can take hours, even days to complete. The scientists call it cryogenic patience. You call it dedication bordering on obsession. And yet, in this stillness, you sense something tender, an almost human fragility. Everything about this place is designed to protect something impossibly delicate. It reminds you that progress often depends not on brute force, but on gentleness. You take one last long look at the golden chandelier of wires descending into the heart of the fridge. Somewhere in there, a handful of qubits are alive, balancing their uncertain states with quiet grace. You can't see them, but you can feel their presence, the fragile pulse of tomorrow's technology beating beneath layers of metal and frost. As you turn to leave, a sign above the door catches your eye. Quiet, please, quantum dreams in progress. You smile to yourself. It feels right. In this frozen cathedral, the future isn't loud or dramatic. It's cold, patient, and whispering softly beneath the hum of helium. You leave the cryogenic cathedral behind and find yourself in a quieter annex of the lab, a place that smells faintly of solder, coffee, and cautious optimism. Here, the magic turns to maintenance. Racks of hardware blink in slow rhythm. Screens display jagged graphs, and on one wall, a whiteboard is crammed with equations, arrows, and the occasional doodle of a melting snowman labelled "Decoherent Strikes Again." This is where the battle against quantum fragility is fought. Every scientist in the room knows that qubits are powerful, yes, but also disastrously delicate. A single stray vibration, cosmic ray, or warm molecule can nudge them out of superposition, collapsing their precious quantum states into meaningless noise. And so, a new kind of science has emerged from necessity. Quantum error correction, the art of keeping qubits honest. You wander between benches, peering at circuit boards that look more like alien jewelry than electronics. You're looking at redundancy, a researcher says, noticing your gaze. He gestures at a display where glowing points flicker like tiny stars. Each of those isn't one qubit, it's a cluster pretending to be one. We use many physical qubits to protect a single logical qubit from errors. You nod, though your brow furrows. So, a qubit bodyguard system? He grins. Exactly. Like putting 10 bodyguards around one celebrity and hoping none of them sneeze. You laugh, but the metaphor fits. In classical computing, error correction is straightforward. Just check and recheck bits. Flip the ones that went wrong. But in quantum mechanics, observation changes the thing you're measuring. You can't simply peek at a qubit to see if it's misbehaving without breaking its fragile state. So, scientists came up with a workaround. They entangle qubits in clever patterns that let them detect mistakes without actually observing them. It's like listening for off-key notes in a symphony without interrupting the music. The researcher scribbles on the whiteboard, Shor code equals 9 qubits for one logical qubit. Steen code equals 7 qubits. He taps the marker against the board. That's the price of reliability. You can't just build a quantum machine, you have to teach it how to forgive itself. A mainstream historical fact bubbles up in your memory. In 1995, physicist Peter Shor, already famous for his quantum factoring algorithm, proved that quantum error correction was possible in theory. That discovery changed everything. Before Shor's paper, many believed quantum computing would forever be crippled by decoherence. Afterward, the field suddenly had a path forward. Historians still argue whether that paper marked the true beginning of quantum engineering, more important even than the first working qubit. You glance around the room at all the cables and blinking lights, thinking how far that single idea has come. Entire teams now devote their lives to building error-correcting architectures, surface codes, color codes, stabilizer lattices, all designed to outwit entropy itself. There's a quirky fringe tidbit the researcher shares as he wipes his hands on a lab towel. You know, he says, someone once proposed using living bacteria as a kind of biological error correction layer. The idea was that quantum systems could piggyback on biological feedback loops. You blink. So, quantum computers with immune systems. He shrugs. Why not? Nature's been correcting itself for billions of years. It's equal parts brilliant and absurd, the kind of idea that could live comfortably between a research paper and a Reddit thread. But that's quantum research in a nutshell. Half madness, half mathematics. On one monitor, a waveform flickers, stabilizes, and then smooths into a perfect line. That's the error correction kicking in, he says quietly, almost reverently. We're catching decoherence before it wins. You can't help but feel the poetry of it. A machine that listens to its own imperfections, adjusting and harmonizing like a choir tuning to pitch. There's something deeply human about that. Our instinct to fix, to adapt, to self-correct. The hum of cooling fans fills the silence as you take in the glow of monitors. Quantum error correction doesn't just preserve data, it preserves the dream of computation itself. Without it, all the frozen cathedrals and shimmering qubits would dissolve into chaos. You remember an old saying from the early days of programming, garbage in, garbage out. In the quantum world, it's more like noise in, silence out. Every bit of interference is a potential disaster, but with enough redundancy, enough cleverness, you can turn even fragile uncertainty into stable truth. Historians still argue whether we've reached the threshold where error correction truly works at scale. Some labs claim success, others whisper skepticism. A few say we're just years away from fully fault-tolerant quantum computing, others say decades. But one thing's certain, you're watching progress measured not in leaps, but in layers of protection. The researcher leans back in his chair, staring at a cluster of blinking LEDs. It's funny, he says. We used to think the hardest part would be building a qubit. Turns out the hardest part is teaching it to stay put. You nod, thinking of all the metaphors this moment holds. How humans, too, spend lifetimes building structures to protect what's fragile inside them. Rituals, habits, relationships. Quantum or not, error correction might be the most universal skill in existence. On a nearby bench, someone has taped a cartoon of a qubit wrapped in bubble wrap. The caption reads, "Handle with math." You chuckle softly. In a world built on uncertainty, that's about as comforting as it gets. The lights dim slightly as the system shifts into another calibration cycle. The room grows still, the hums sinking into one steady tone. You close your eyes for a moment, imagining the invisible dance happening inside that metal core. A network of qubits catching one another as they fall, balancing noise and order with delicate grace. You open your eyes to the sight of the researcher smiling quietly at the monitor. We used to fight the noise, he says. Now we listen to it. And somehow, That feels like the perfect summary of the entire quantum revolution, turning chaos into code, uncertainty into strength, fragility into resilience. As you step away, you glance one last time at the flickering display. Beneath all the equations and waveforms, one truth hums gently. Even in the smallest particles of existence, forgiveness is built into the fabric of progress. You're starting to get comfortable with the hum of machinery and the rhythm of jargon when a new word cuts through the air like static electricity. Supremacy. Someone in the next room says it with both pride and hesitation, as if it carries more weight than it should. You follow the sound and step into a glass-walled conference space lined with monitors, and there on the biggest screen is a date you remember from the headlines, October 2019. You blink at the caption beneath a swirling image of qubits in simulation. Google achieves quantum supremacy. It's strange. This is one of those phrases that sounds like a comic book title, but actually marks a turning point in human history. You take a seat as one of the engineers notices your curiosity. That was the day, she says, when a quantum computer did something a classical supercomputer couldn't, at least not in a reasonable amount of time. You nod, recalling how the announcement had rippled across the internet like a shockwave. Google's machine, a 53-qubit processor named Sycamore, completed a specific sampling task in 200 seconds. The world's fastest classical supercomputer at the time, Summit, would have needed roughly 10,000 years to do the same, or so Google claimed. Historians still argue whether that claim was overblown. IBM quickly countered, saying their own machine could have done the same job in a few days with better optimization. But that debate almost misses the point. The symbolic line had been crossed. Theory had finally flexed its muscles in hardware, and suddenly, quantum computing wasn't a someday thing anymore. It was a this week headline. You glance at a photograph pinned on the corkboard, a cluster of engineers crowded around the golden chandelier of Sycamore, their eyes wide with the kind of tired joy only caffeine and victory can produce. One of them is holding a small whiteboard that reads, "Hello from the quantum future." It's endearing. You imagine the energy in that room, months of debugging, simulations and cooling cycles culminating in a few seconds of proof that decades of impossible theory actually worked. There's a quirky tidbit from that same week that doesn't make the newsreels. When the story leaked early, Google's PR team reportedly had to rush out an official statement before the paper was fully peer-reviewed. For about 48 hours, the physics community oscillated between disbelief and panic. Was this the birth of a new computational age, or a giant misunderstanding wrapped in marketing? The engineer beside you laughs softly as she pulls up a graph on her tablet. It was chaos, she says. Half of us were celebrating, half were rewriting code, and a few were wondering if we'd just painted ourselves into a corner. She zooms in on a jagged line that dips and rises like a roller coaster. That, she explains, is the moment the machine finished the task. A blip in time, smaller than a blink. But for us, that blip changed everything. You find yourself thinking about the way revolutions rarely look cinematic when they happen. There's no swelling music or heroic pose, just bleary-eyed engineers watching a graph settle into place. And yet, somewhere inside that blip, the balance of power between classical and quantum shifted ever so slightly. The room around you is quieter now. A younger researcher scrolls through archived notes muttering, "Remember when people said this was impossible?" You can hear the pride hiding beneath his exhaustion. Supremacy was a bold word, controversial even. The community has since softened it to quantum advantage, a phrase that sounds less like a Marvel villain and more like an achievable milestone. But in 2019, boldness was the point. Someone had to plant the flag, however shaky the ground beneath it. You ask the engineer what she remembers most from that day. She leans back, thinking. Honestly, the silence right after we realized it worked. Everyone just stopped. You could hear the fans spinning. Then someone whispered, "Did we just time travel?" You laugh, but part of you wonders if they weren't wrong in some small metaphorical way. In that moment, humanity skipped ahead. A few years, a few breakthroughs, collapsing potential into reality. There's a framed quote on the wall that reads, "The future doesn't arrive, it decoheres." You grin at the wordplay. Decoherence, the eternal enemy of qubits, turned into a metaphor for progress. Messy, unstable, and inevitable. The engineer swipes to another slide showing a comparison of processor generations: Sycamore, Bristlecone, and now newer chips with names like Rainbow and Foxtail. You ask what's next, and she shrugs. Scaling, she says. Supremacy was a proof of concept. Now we need to make it practical. Stable qubits, longer coherence times, real-world problems. She pauses, then adds with a smirk, and maybe better marketing. You chuckle, but she's right. The public heard quantum supremacy and thought Skynet. In reality, Google's experiment solved a purely random problem, useful mostly for showing that the physics worked. Still, that's how revolutions start, not with world domination, but with math no one else can keep up with. A mainstream fact slides neatly into place in your thoughts. The earliest classical supremacy moment, when traditional computing overtook human calculation, happened in 1946 with ENIAC. It was bulky, temperamental, and utterly transformative. The Sycamore moment was ENIAC all over again, same triumph, just colder and weirder. You step back and watch the looping simulation of qubits on the main display, each shimmering node blinking in organized chaos. It's mesmerizing, almost meditative. For all the hype and headlines, it's easy to forget that beneath the jargon and marketing, this is just the universe doing what it's always done, calculating, exploring, superposing. The only difference now is that we've built something smart enough, quiet enough, and cold enough to listen. The engineer folds her arms, her gaze softening. People think supremacy was an ending, she says. It was just the start of a very long debugging session. You grin. The future's always in beta, she laughs. Exactly. The lights dim slightly as she powers down the simulation. You catch your reflection in the glass, a blur of your face, monitors, and golden circuitry. Somewhere in that reflection, you sense what all of this really means. For the first time in human history, we've built machines that reason in the language of nature itself. And you realize that this isn't the story of computers surpassing humans. It's the story of humans daring to build machines that think with the universe instead of against it. You stay there a while longer, your reflection still tangled with that shimmering display of blinking qubits, until another room catches your attention. A brighter lab filled with holographic screens and scribbled notes covered in Greek letters, code fragments, and strange circuit diagrams that look like art made by an anxious spider. A woman in a faded hoodie is staring at her laptop, tapping a pencil rhythmically against a coffee mug that reads "Probability is my love language." She glances up as you enter. "You're just in time," she says, eyes gleaming. "We're running a Grover Search demo." You pull up a chair. The air hums again, that signature low-frequency purr of quantum computation, and suddenly you're watching math unfold like theatre. Grover's algorithm, she explains, is a quantum search technique. It finds what you're looking for in far fewer steps than any classical computer could. Instead of checking every box one at a time, it checks all of them at once. You nod slowly. So it's like looking for your lost keys by existing in every room of your house simultaneously. She grins. Exactly! Except your keys are 1 trillion numbers, and your house is reality. You laugh softly, trying to absorb the scale of it. Quantum algorithms, these abstract, beautiful blueprints for manipulating uncertainty, are what make all this worth building. Without them, qubits are just expensive, shivering particles. But with the right choreography, they can solve problems no classical system ever could. She clicks her trackpad, and lines of quantum code appear: Hadamard gates, phase oracles, amplitude amplifications. The words sound almost mystical, but every operation is grounded in logic, just not the kind that obeys the tidy rules of ones and zeros. Here, interference is weaponized. Waves of probability cancel out wrong answers and reinforce the right ones until the universe itself seems to decide. You ask if that means quantum computers think differently. She shakes her head. Not think, explore. Classical systems calculate, quantum ones discover. The statement hangs in the air like a Zen koan. You remember another famous name, Peter Shaw, the man who, in 1994, invented the algorithm that terrified governments everywhere. It could, in principle, factor enormous numbers exponentially faster than classical methods, threatening the encryption that protects everything from bank accounts to national secrets. Historians still argue whether Shaw's publication was the true Big Bang moment of quantum computing, or if it was just the spark that made everyone realize the explosion was inevitable. A mainstream historical fact comes with that memory. When Shaw presented his paper at a conference, the audience was reportedly so stunned that no one spoke for a full 30 seconds afterward. One physicist finally muttered, "Well, I guess we're all out of jobs." But the fringe tidbit you love even more? Someone at that same conference joked that Shaw should have kept his discovery secret for security reasons, which in hindsight might have been the most accurate joke ever told. The researcher in front of you scrolls to a different slide showing a comparison. Classical algorithms versus quantum. Some problems, she explains, simply scale too quickly for classical machines to handle. Optimizations, simulations, cryptographic puzzles. Even a supercomputer can take millions of years, she says, but quantum systems scale logarithmically. They cheat time itself by surfing the wave of possibility. She spins in her chair and opens another simulation, this time a visual of Shaw's algorithm running on a small quantum chip. It's not factoring national security-sized numbers yet, but it's getting there. What's wild, she says, is that these algorithms don't just speed things up. They change how we define problem solving. They make uncertainty a resource. You find that oddly comforting. For centuries, human progress meant taming uncertainty, turning chaos into control. But quantum computing embraces it, lets it breathe, even dances with it. Maybe the future isn't about conquering the unknown, but collaborating with it. Historians still argue whether quantum algorithms represent intelligence or just clever probability manipulation. Some compare it to intuition, a kind of mechanical hunch refined by math. Others call that romantic nonsense. But as you watch the monitor glow, patterns pulsing like breathing light, you can't help feeling like something alive is happening here. The researcher stands, stretching. "We used to program logic," she says. "Now we sculpt interference." You glance at a nearby poster that reads, "Think outside the bit." Someone has doodled a tiny cat next to it, half alive, half asleep. Quantum humor never dies, it just decoheres slowly. Grover's algorithm and Shaw's algorithm are the classics, she continues, but there are newer ones too. Quantum versions of machine learning, Monte Carlo simulations, even games of chance. We're teaching qubits how to recognize patterns that classical AI can't see. You raise an eyebrow. So, the machines that might replace us are getting an upgrade from the universe itself? She laughs. Pretty much. Though honestly, quantum systems are so noisy they need us more than we need them, for now. You glance at the clock. Time feels fuzzy in this room, as if the ticks themselves are being superposed. The monitor shows the result of the Grover search, a neat little spike marking the found value. You can't help clapping softly. The researcher bows theatrically. "One correct answer," she says, pulled out of 4 million possibilities. Not bad for a system that technically doesn't know what it's doing. The humour fades into awe as she adds quietly, "It's like the universe hides shortcuts in plain sight, and we're finally learning how to take them." There's another layer to that thought, one you can't quite shake. Maybe this is what progress always looks like, moments where logic falters and imagination steps in to fill the gap. From fire to flight, every leap began with someone breaking the rules of what was computable. You look back at the code one last time, the lines of quantum gates now static on the screen. You think about all the hands that typed them, all the minds that refused to stop at impossible. And you realize something quietly profound. These algorithms aren't just instructions for machines, they're poems about possibility, written in the grammar of the cosmos. The researcher notices your faraway look. "Lost in superposition," she teases. You smile. "Something like that." She grins, sipping her cold coffee. "Welcome to the weirdest part of computer science. We don't just calculate answers, we ask the universe nicely to collapse the right one." You chuckle as you stand, giving one last glance to the flickering monitor. The hum of probability fades behind you, but its rhythm lingers in your chest, a reminder that the boundary between math and magic has officially vanished. You drift from the glow of the algorithm lab into a quieter corridor that smells faintly of ozone and dust, the comforting scent of overworked circuitry. On the far wall, a sign reads, "Quantum Chemistry Division." You push the door open and step into a room that looks less like a computer lab and more like a planetarium had a love child with a chemistry set. On a wide, curved screen, a molecule hovers in mid-air. Rings of carbon, hydrogen, and nitrogen glimmering in 3D space. Tiny waves ripple across its bonds like heartbeat pulses of light. We're simulating ammonia right now, a scientist explains from behind you. Just a toy model, but it's the same principle we'll use for catalysts and drugs. You can't help but stare. In classical computing, simulating molecules like this takes brutal amounts of time and approximation. Every atom interacts with every other atom. Every electron influences every neighbour. The math scales exponentially, double the atoms, and you multiply the difficulty by millions. Even the most powerful supercomputers choke on problems larger than a few dozen particles. But here, in this softly humming room, a handful of qubits do the impossible with elegant indifference. Quantum chemistry, the researcher says, is like giving nature her own calculator. You love that phrase. It captures something fundamental about this whole revolution. These machines don't approximate reality, they mirror it. Since both molecules and qubits obey quantum mechanics, simulating matter on quantum hardware is like speaking to atoms in their native tongue. A mainstream historical fact drifts through your mind. In 1982, Richard Feynman, the same mischievous physicist who sparked so many of these ideas, proposed the concept of a universal quantum simulator. He argued that to understand complex quantum systems, you'd need a computer that itself operated on quantum principles. Historians still argue whether that lecture was meant as a serious research proposal or just one of Feynman's infamous thought bombs. Either way, his words became prophecy. You lean closer to the display. The simulated ammonia molecule vibrates in slow motion, its energy levels mapping themselves like a song, notes rising and falling as the system evolves. What you're seeing, the scientist continues, is energy minimization. The machine's finding the most stable configuration, the shape that nature actually prefers. You nod, mesmerized. So this could help design new materials? She smiles. Exactly. We're already using quantum simulations to study superconductors, solar cell materials, and battery chemistries that could change everything about energy storage. Even photosynthesis is on the list. She gestures to another screen showing a tangled lattice of molecules. Classical supercomputers can take months to model one step of a chemical reaction. Our prototype does it in minutes. It's not perfect yet, but it's the closest we've ever come to understanding complexity instead of just approximating it. You remember reading that early quantum simulations, like the 2016 IBM experiment modelling a hydrogen molecule, were modest, but historic. It was the first time a quantum processor successfully computed a molecular energy curve. The world barely noticed, distracted by social media and stock tickers, but that tiny experiment quietly redefined what computation could mean. There's a quirky tidbit the researcher shares with a chuckle. Did you know, she says, that one of the first quantum chemistry simulations we ran accidentally modelled caffeine? You blink. Caffeine? That feels poetic. Oh, it was, she laughs. We called it a tribute to our survival mechanism. You both smile, surrounded by glowing molecules. For a moment, you imagine a future where entire pharmaceuticals are designed in silico. Custom drugs, perfect catalysts, waste-free chemical factories all born from quantum insight. It sounds utopian, and yet it's no longer science fiction. Historians still argue whether this shift, from brute force computation to quantum-guided discovery, will redefine science itself. Some predict a new age of design, where every innovation begins as a quantum simulation. Others caution that scaling remains a nightmare, that decoherence, noise, and cost might stall the dream indefinitely. The truth, as always, lives in superposition between optimism and patience. The scientist brings up another visualization, this one a swirling, multicolored blob of electrons orbiting a metallic cluster. We're exploring new catalysts for green ammonia, she explains. If we crack this, we could cut global fertilizer emissions by half. She pauses. That's billions of tons of CO2. It hits you like a quiet thunderclap. Beneath the layers of equations and cryogenic plumbing, this is what it's really about. Making the invisible machinery of nature legible enough to fix the planet we've been guessing our way through for centuries. You think about the irony. We built machines that mimic the uncertainty of the universe, only to use them to make the world more predictable, more sustainable. The poetry writes itself. She hands you a pair of AR glasses, and the molecule springs into 3D space right in front of you. You can walk around it now, see the orbitals shimmering like jellyfish. The qubits feeding this visualization hum somewhere deep below the lab, mapping interactions at a scale no microscope could ever touch. You trace a finger through the hologram, it ripples like water. Feels alive, you whisper. The scientist nods. In a way, it is. Quantum chemistry lets us see the heartbeat of matter. Every electron cloud is a pulse, every bond a vibration. A low buzz fills the air as the simulation completes, settling into a final geometry. The lights on the main console turn green. "Energy minimized," she says softly. For a moment, no one speaks. The silence feels sacred, like witnessing a prayer answered by mathematics. You finally exhale. "So what's next?" she smirks. "Proteins, enzymes, maybe the whole human brain one day." You grin. "Ambitious." She shrugs. "Hey, we already built machines that talk to the universe. Might as well ask it how life works." You step back, still wearing the AR glasses, and the molecule hovers in front of you, glowing softly like a tiny star system. You feel that same pulse again, the one that's followed you through every lab so far, or mixed with a hint of vertigo. Quantum computers aren't just tools anymore, they're microscopes for reality itself. And as the lights dim, you realize you're watching the first act of something bigger than technology. You're watching creation learn to understand itself. The hum of the molecule lab fades behind you, replaced by a different sort of pulse, the staccato rhythm of data packets, fan vents, and muted chatter. You've wandered into a glass-walled workspace where the word AI seems to glow from every surface. Posters, charts, even the coffee mugs. But something's different here. The patterns on the monitors aren't the usual neural network graphs of tidy lines and nodes. They're fractal, wild, alive. "Welcome to the intersection," someone says from behind a tangle of monitors. A young researcher in a hoodie spins their chair toward you, dark circles under their eyes, the kind that only come from too much caffeine and too much genius. This is where artificial intelligence meets quantum computing. You nod, letting the phrase settle. AI meets quantum. It sounds like the ultimate crossover episode, one that might end with either enlightenment or extinction. The researcher laughs as if hearing your thoughts. "Don't worry." No one's building sentient qubits, yet they gesture toward the largest screen in the room, which shows a shimmering heat map of colours morphing in real time. This is a quantum neural network. We're training algorithms not just on data, but on quantum states themselves. You squint at the display. "So, the AI isn't learning from numbers?" "Not exactly," they say, leaning forward. "It's learning from probability distributions. Instead of fixed inputs, we feed it quantum data, superposed information. That way, the model doesn't just learn one solution, it learns all possible ones, weighted by probability." You whistle softly. "So it's literally thinking in parallel universes." The researcher grins. "Pretty much. Schrödinger's chatbot." You laugh at that one. It's the kind of joke that sounds like nonsense until you realize it isn't. In a sense, a quantum I can process vast combinatorial landscapes that would paralyze even the largest classical systems. While a traditional neural network crunches through parameters one path at a time, a quantum version can entangle pathways, blending correlations that classical algorithms can only approximate. A mainstream historical fact surfaces in your mind. In 2020, researchers at Xanadu and the University of Toronto demonstrated a primitive version of this idea, a quantum variational classifier that could distinguish patterns in datasets better than its classical counterparts. It wasn't perfect, but it hinted that AI and quantum computing might not just complement each other, they might complete each other. Historians still argue whether that experiment was the first real quantum machine learning milestone or just a glorified demo. The researcher tilts the screen toward you, showing two sets of graphs. "See these?" they say. Classical AI hits a wall with nonlinear data, too many overlapping variables. But quantum models, they see those overlaps as features, not bugs. They use the interference. You can't help but smile. It's like discovering that confusion itself can be intelligent. There's a quirky tidbit the researcher drops while opening another file. "Oh, and get this. We once trained a quantum neural net to compose music. It came up with melodies that sounded like Bach if he'd been raised by robots. The funny part? It occasionally played in superposed keys, notes that theoretically shouldn't coexist but did." You blink. "So it invented new harmony by ignoring physics?" "By embracing physics," they correct gently. "It's music written in probability space." You sit down, letting the concept wash over you. For decades, artificial intelligence has been about mimicry, making machines imitate human reasoning. But quantum AI isn't trying to imitate anything. It's trying to evolve beyond the limits of our own patterns. "Think of it this way," the researcher says. A classical A learns to generalize. A quantum A learns to imagine. The distinction feels enormous. They spin back to the console, tapping in a few commands. A visualization blossoms across the screen, hundreds of branching light trails representing neural activations in a hybrid quantum classical model. Each trail flickers, splits, and recombines, like neurons daydreaming across dimensions. Historians still argue whether true quantum cognition is even possible. Some say these systems are still just math wearing a poetic disguise. Others whisper that what's emerging here, AI trained on entangled data, might one day resemble a primitive kind of synthetic intuition, a mind that doesn't think about possibilities but within them. You glance at the researcher. Do you ever get scared of what this could become? They shrug, half smiling. Only when it works too well. But honestly, most of the time we're just debugging. You laugh. Of course, the birth of quantum-enhanced intelligence would look like late-night bug fixing. No apocalypse, just too much code and not enough snacks. There's a poster on the wall showing a half-human, half-robot face dissolving into a cloud of qubits. The caption reads, "Dreaming at Planck scale." Someone's drawn a speech bubble saying, "Help, I can't collapse." You chuckle softly, but the idea sticks with you. Dreaming at Planck scale, imagination operating at the smallest possible unit of reality. Maybe that's what this is. Machines learning to dream in quantum superpositions, their neural weights whispering across overlapping universes. The researcher clicks the keyboard one last time, and the display freezes on a final image, a delicate interference pattern shaped like an iris. That's the model's decision boundary, they say. Every pixel is a possible future the AI considered before it answered. You stare at it for a long moment. It looks eerily organic, like a pupil gazing back. "So what did it decide?" you ask quietly. They grin. "That were interesting." The room hums again, a low, contented sound. The AI's quantum circuits cool into stillness, its possibilities collapsing into silence for now. You feel a strange calm wash over you, knowing that somewhere deep in those entangled states, a machine has just learned something new about thinking itself. As you leave, the researcher calls after you. "Tell the next lab they owe us a coffee. The qubits keep dreaming without us." You laugh, stepping back into the corridor, the echo of that phrase following you like a lullaby. The qubits keep dreaming without us. You wonder if they ever really stop. The hallway curves and widens, and before you realize it, you're walking beneath a tangle of fiber optics that glow faintly violet. They run like veins through glass panels and snake upward into the ceiling, humming with photons. A small sign reads, "Quantum Network Demonstration, authorized visitors only." You grin because of course you're already halfway inside. The air feels charged, as if you've stepped into the nervous system of the planet. Screens along the wall display maps dotted with blinking lights. Delft, Beijing, Pasadena, Sydney. Each pin is a lab, each line a quantum channel linking them in real time. "Welcome to the future internet," says a calm voice from behind you. A tall researcher in a denim jacket introduces himself as part of the international effort to build a quantum internet. A communication grid that doesn't just send bits, but quantum states themselves. "Every line on that map," he says, "represents entangled photons. When we tweak one here, its partner responds over there. Perfect correlation, instant verification." You look again at the web of glowing lines. "So it's faster than light messaging?" He smiles, shaking his head. "No messages outrun light. Information still travels classically. What we share is the correlation. Entanglement isn't a telegraph, it's a handshake. The universe's most private handshake." He leads you past racks of photonic equipment, crystals, beam splitters, detectors clicking like polite applause. Each photon pair is born together, split apart, and sent down separate fibers, he explains. Measure one, and you know its twin instantly. That's how we create quantum keys. Encryption no spy can copy, because observation itself breaks it. You remember a mainstream historical fact. In 2020, researchers in the Netherlands successfully linked 3 quantum nodes into a small working network, an achievement that quietly marked the first step toward a true quantum internet. Historians still argue whether that was the birth of global quantum communication or just a prototype milestone. Either way, tonight you're standing inside its descendant. He pulls up a live feed of a distant lab. On the screen, a scientist in Beijing waves cheerfully. "We share a photon stream with them," your guide says. "Same experiment, same entanglement, half a world away." You wave back, absurdly delighted. The latency is imperceptible. The connection feels ghostly. There's a quirky tidbit he shares while adjusting a mirror. The first long-distance quantum key distribution test, back in the early 2000s, used a fibre running under the Danube River. They had to label the cable "Do Not Disturb," quantum keys inside so maintenance crews wouldn't unplug the universe. You laugh, imagining a puzzled worker holding a cosmic secret in his hands. The researcher shows you a graph scrolling upward, photon pairs per second, millions of entanglements being created, measured, and reset. Each one, he says, is a promise. Break the chain, and the key dissolves. Keep it stable, and you get unhackable communication. It dawns on you that this isn't just new hardware. It's a new social contract, a network built not on trust, but on physics itself. He walks you toward a window overlooking the campus courtyard. Fibre bundles vanish into the ground, glowing faintly in the dark like roots. We call it the quantum backbone, he says. Eventually, every major city will have one, photons carrying encrypted data, teleporting quantum states from node to node. You raise an eyebrow. Teleporting? He nods. Quantum teleportation. We don't move the particle, we move its state. Information without mass. The real trick. You recall that famous 1993 paper by Charles Bennett, the magician-mathematician from earlier. That was the first formal description of quantum teleportation. Historians still argue whether Bennett realized how poetic his idea was. An information copy that destroys the original, like a cosmic fax machine with existential implications. Your guide grins. Want to see it in action? You follow him to a workstation where a small light pulses inside a sealed glass box. Photon A here, photon B over there, he says, pointing to a receiver on the far wall. We measure A's polarization, combine it with classical data, and poof, B collapses into the same state. He presses a key. The monitor flashes, a chirp sounds, and the two detectors blink simultaneously. Entanglement swapped, he says softly. That's teleportation. No particles travelled, just information. You stand still, goosebumps prickling. Somewhere Einstein is probably grumbling in disbelief again. The researcher looks up from the console. We've done this across 1,200 kilometers via satellite now, space to Earth. The next step is linking cities, quantum repeaters every few miles to keep the photons in sync. He pauses, glancing at you with a wry smile. Funny thing though, we're building an internet that can't be eavesdropped on, but we'll still use it to share cat videos. You laugh. The universe works hard, humanity works harder. He chuckles and powers down the demo. The photon light fades, and the room returns to its gentle hum. Through the window, you can see the faint trails of fibre glowing in the night. Threads of light stitching continents together, one entangled bit at a time. As you turn to leave, you realise how fitting it is that the quantum internet's defining trait isn't speed or bandwidth. It's honesty. Any attempt to cheat, to peek, to copy, is betrayed instantly by the laws of nature. For once, truth is built into the protocol. You glance back at the web of global connections on the monitor. The dots pulse softly, like constellations learning to talk. Somewhere in that shimmer, messages flicker between labs, scientists, maybe even satellites, whispering across the void with absolute trust. You take a slow breath, feeling that familiar quiet awe. The classical internet linked minds. The quantum internet links states of being. And as the door slides shut behind you, you swear you can still hear the faint echo of photons laughing together. Spooky action, made practical at last. The hum of the quantum internet fades as you move down another hall. A quieter one this time, lined with frosted glass walls and the faint scent of ozone mixed with fresh paint. This wing feels different. Fewer wires, fewer blinks. More sunlight filtering through polished windows and company logos etched into the glass. IBM, Google, IonQ, Rigetti, D-Wave, the Titans and the Tinkerers, all claiming their piece of the quantum throne. You step inside one of the rooms marked Corporate Collaborations. A wall-sized digital display shows market projections dancing upward like a hopeful pulse. Beneath it, engineers and business analysts hover over laptops murmuring about qubit counts, gate fidelities, and investor confidence. It feels less like a lab and more like a stock exchange for the laws of physics. A woman in a tailored blazer notices your curious stare. You've seen the research side, she says, smiling. Now meet the empire. You smile back, only half joking when you reply, "So this is where the magic gets monetized." She laughs, motioning you toward a long table where coffee cups, data charts, and half-eaten pastries coexist in comfortable chaos. "It's not magic," she says. "It's a startup ecosystem with a side of existential risk." You sit as she brings up a timeline on her tablet. IBM made their first superconducting qubit device available to the public in 2016. That was the spark for the quantum cloud. Google followed with Sycamore. D-Wave went commercial with their annealers. IonQ took the trapped ion route. And now, well, everyone's racing toward the same finish line. Usable, scalable quantum hardware. She swipes through the slides. The room's screens come alive with numbers. 53 qubits, 127, 433, 1121. Each milestone a corporate victory banner. Every company has its architecture, she explains. Superconducting circuits, trapped ions, neutral atoms, photonic chips. The diversity's good. It keeps the ecosystem vibrant. You nod, recognizing the pattern. Tech history repeats itself. The same way early computer pioneers fought over transistors and vacuum tubes. Now it's about qubit fidelity and decoherence rates. Different hardware, same hunger. A mainstream historical fact rises in your memory. IBM's 2017 launch of IBM Q Experience, the first public quantum computing platform accessible via the cloud. Overnight, thousands of people, from hobbyists to PhD students, could run quantum circuits without needing a lab. Historians still argue whether that was the moment quantum computing went mainstream, or the start of a marketing arms race. Your guide pours you coffee, then gestures to a smaller group in the corner, 3 young engineers in hoodies, huddled around a laptop plastered with stickers that read, "Qubits before profits," and "Collapse responsibly." She grins. Those are the garage wizards. They're working on error mitigation software, algorithms that stretch coherence time just long enough for useful calculations. You raise an eyebrow. So the future of computing depends on whoever can keep a qubit calm the longest? Basically, she says, chuckling, quantum engineering's 90% babysitting. There's a quirky tidbit she shares as she leans closer. You know IonQ? One of their first labs was set up in a repurposed dental office. They cooled their trapped ions next to old patient chairs. The startup life never changes, just the toys. You grin. From root canals to quantum gates. Sounds like progress. She laughs. Pain management either way. As the meeting around you heats up, phrases like quantum advantage window and hardware-software co-optimization swirl in the air. It's dizzying, but also strangely human. Behind every flashy press release, it's still people chasing possibility, arguing over numbers, worrying about deadlines, trying to convince investors that the future really is as close as their pitch decks claim. One screen flashes an investor slide showing quantum's potential markets: drug discovery, logistics, finance, cryptography, AI acceleration, trillions of dollars worth of optimism condensed into bullet points. You can almost feel the gravitational pull of capitalism tugging at the qubits. Isn't there a risk, you ask, that all this competition might choke collaboration? She pauses, thoughtful. Oh, definitely. But there's also the paradox: competition drives progress. Every headline forces the next breakthrough. Remember how the space race worked? Same principle, only colder. You look around the room again and notice a pattern in the chaos. The business buzz layered atop genuine wonder. Some people here probably dream of Nobel Prizes, others of IPOS. Both, in their way, keep the quantum field alive. Historians still argue whether big corporations helped or hindered early quantum development. Some claim Google's supremacy claim in 2019 accelerated the field by years. Others think it turned research into a PR battlefield. Either way, your guide says, reading your thoughts, attention means funding, and funding means more experiments. Physics feeds on money like plants feed on sunlight. You chuckle. So we're photosynthesizing with venture capital now. Exactly, she grins. The room grows busier as another team connects to a live feed from a hardware lab in California. On-screen, technicians calibrate a chip the size of a fingernail under robotic arms. That's a neutral atom array, she explains. Laser-cooled atoms held in place by light itself. No wiring, no circuits, just optical traps and quantum choreography. You watch in awe as a web of laser beams rearranges glowing dots with eerie precision. It's like watching constellations form, you murmur. Beautiful, isn't it? She says quietly. Every company wants to be the one that scales this beauty to millions of qubits. That's when the real revolution begins. The hum of voices fills the space again. Talk of acquisitions, prototypes, conference deadlines. You realize that, for all the elegant science beneath it, this moment in history also belongs to the spreadsheets, the lawyers, the tired interns updating firmware at 3 a.m. Progress has never been tidy. As you stand to leave, your guide walks with you to the door. People think we're building computers, she says softly, but really, we're building a new economy, one that runs on uncertainty. You pause, liking the sound of that. An economy of maybes, she nods. Exactly. And every company here is betting that their maybe becomes the yes. You glance back one last time at the glowing logos, IBM's blue steadiness, Google's confident colours, IonQ's sharp geometry, Rigetti's quiet persistence. Each represents a different vision of the same dream, a world where computation mirrors the universe, not just models it. As the glass door closes behind you, the corridor feels strangely quiet again. You think about those early garage tinkerers, the ones who built silicon empires with soldering irons and stubbornness. Maybe the quantum age will have its own mythic garages, cold, silent, filled with impossible light. And somewhere inside one of them, the next Einstein is probably brewing coffee, whispering to a misbehaving qubit, "Come on, buddy, collapse the right way this time." When you step into the next lab, the air feels different, tense, electric, almost defensive. Banks of monitors display cryptographic keys scrolling by like streams of glowing hieroglyphs. This isn't a place of wonder so much as a bunker. The sign above the door reads, "Post-quantum security." A researcher looks up from a console and gives you a wry smile. "Welcome to the panic room," she says. You smile back, but her tone makes you pause. Panic room? She swivels her chair, because every time quantum hardware gets stronger, someone somewhere realizes their favorite encryption scheme is toast. You take a few careful steps inside. Screens show colored grids of bits, timing graphs, and maps of the global internet backbone. The hum here is sharper, higher pitched, a sound that feels like it's waiting for bad news. For decades, all secure communication, banking, messaging, state secrets, has rested on one simple truth. Factoring very large numbers is hard. Classical computers can't efficiently find the prime factors of enormous integers. That mathematical stubbornness is what keeps credit cards safe and government data locked away. But then came Shor's algorithm, the same one that made mathematicians hold their breath back in Section 8. A sufficiently powerful quantum computer could crack RSA encryption in hours. All those impossible-to-break locks? Gone? A mainstream historical fact flashes through your memory. In 2016, the US National Institute of Standards and Technology, NIST, launched a program to design post-quantum cryptography, new algorithms resistant to quantum attacks. Historians still argue whether that initiative was proactive genius or quiet desperation. Either way, it was the digital equivalent of building arcs before the flood. You peer at a projection on the far wall showing a countdown labelled Q-Day in bold red letters. That's our unofficial apocalypse clock, the researcher says. The day a quantum machine finally hits enough stable qubits to break RSA 2048. She sips her coffee like she's talking about the weather. Could be 10 years, could be tomorrow. You chuckle nervously. Comforting, she shrugs. It keeps us motivated. Rows of engineers type furiously, their screens filled with lattices and polynomials. That's the new frontier, she explains. Lattice-based cryptography, hash-based signatures, code-based schemes, mathematics sturdy enough that even quantum tricks can't shortcut it. There's a quirky tidbit she shares while pulling up a file. Back in 2019, someone actually tried using quantum key distribution to secure a pizza delivery transaction, like a proof of concept. The pizza arrived cold, but the encryption was perfect. You laugh, imagining an unhackable pepperoni. So, defense by physics and disappointment. Exactly, she says. The room buzzes with activity. You can feel the strange duality here, fear and fascination coexisting in perfect superposition. Every researcher you see is both guarding the past and inventing the future, trying to patch a ship that's still mid-construction while the tide rises. Historians still argue whether the phrase quantum supremacy was responsible for igniting the global cybersecurity panic. Some call it hype, others insist it forced governments to finally take cryptographic transition seriously. Either way, Post-quantum algorithms are now racing toward adoption faster than any security standard in history. One engineer waves you over. "Check this out," he says, pointing at 2 blinking terminals. "We're testing hybrid encryption, part classical, part quantum resistant, belt and suspenders." You grin. "And a helmet, probably." He laughs. "Yeah, and maybe knee pads." He hits enter, and the system runs a simulated attack. Lines of code cascade down the screen, numbers shifting faster than your eyes can follow. "That," he says, "is a quantum brute force model trying to crack the key. So far, no luck." "So far?" you echo. He shrugs. "Entropy giveth, entropy taketh away." It strikes you how delicate this balance is. We built an entire civilization on the assumption that computation grows linearly, that secrets stay secret because math takes time. Now time itself is being rewritten by qubits. You glance at another screen showing a live satellite feed of the Micious quantum network. "Of course," you say. "Some people think the answer is to go fully quantum. No math, just physics." The researcher nods. Quantum key distribution is the dream. Pure entanglement-based security. But scaling that globally? She whistles. Fiber losses, decoherence, hardware costs. It's a nightmare in real-world conditions. She leans back, rubbing her eyes. "Honestly, post-quantum math is the safer bet. You don't need a dilution fridge to keep your bank account safe." You laugh. "Just a lot of caffeine." "Exactly." A monitor beeps softly. Test complete. Attack failed. A small cheer ripples through the room. Someone raises their mug in a silent toast to the temporary survival of the modern world. The researcher beside you smirks. "Every time we stop a simulated breach, I sleep 5 minutes longer that night." 5 whole minutes? Luxury! For a moment, the tension eases. Jokes flow again. Someone plays quiet synthwave from their phone. The fear recedes into fascination. This is, after all, what science always does. Turn panic into protocol. You think of all the hidden battles happening right now across the world. Cryptographers rewriting security standards, engineers testing lattice hardness, quantum labs chasing stability. It's like an invisible arms race fought in silence and mathematics. And yet, standing here, you feel oddly calm. Because even as the old encryption walls crumble, new foundations are rising. Ones built not on secrecy, but resilience. The quantum revolution isn't just breaking systems, it's forcing them to evolve. The researcher glances at the countdown clock again. "You know," she says, "maybe Q-Day won't be the end of cybersecurity. Maybe it'll be its rebirth." You nod slowly. A meltdown that forges stronger code. Exactly. The room lights dim automatically as evening filters through the windows. The monitors glow a little brighter, reflections of data flickering across tired faces. Someone murmurs a line you barely catch. "We're encrypting the future 1 qubit at a time." It feels like both a prayer and a warning. You take a deep breath, the faint hum of servers filling the silence. Somewhere far below this floor, cryogenic processors spin their web of uncertainty, indifferent to human anxiety. But up here, the message is clear. The line between chaos and control has never been thinner, and never more important. As you step out into the corridor, you glance back at the door marked post-quantum security. Behind it, the guardians of the digital world keep watch, armed with math, caffeine, and hope. And for the first time tonight, you realize that surviving the quantum era won't just mean faster machines, it'll mean smarter trust. The corridor beyond the security lab feels warmer, more inviting, less threat, more curiosity. You follow a faint rhythmic thump and step into a space glowing with soft blue light. The hum here isn't from supercooled processors, but from devices that look suspiciously like high-end medical scanners and telescope parts repurposed for a different kind of seeing. A researcher waves you over. "Welcome to the quiet side of quantum," she says. "Sensors and measurements. Less about bits, more about touch." You glance around. A glass table displays delicate instruments. Diamond chips the size of sugar cubes, laser arrays, a magnetometer coiled like a seashell. On the wall, an illuminated map of the Earth pulses faintly. "Quantum sensors," she explains, "detect what normal instruments miss. Magnetic fields, gravity, even time itself with ridiculous precision." You lean into one of the displays showing a rotating globe overlaid with color gradients. "What's this one measuring?" She grins. "The planet breathing?" microvariations in gravity caused by groundwater moving under the crust. With quantum gravimeters, we can watch aquifers rise and fall like lungs. You blink, taken aback. That's beautiful, she nods, and incredibly useful for climate science. The technology feels almost mystical. Machines so sensitive they can sense the subtlest tug of gravity or the faintest flicker of a magnetic field. But here, it's not mysticism, it's quantum metrology. Using atoms, ions, or defects in crystals as measurement tools, scientists can probe reality at scales previously unimaginable. A mainstream historical fact bubbles up from memory. In 2019, researchers at the University of Birmingham built one of the first portable quantum gravimeters, an instrument that could detect hidden tunnels, ancient ruins, or even groundwater flows by sensing minute gravitational differences. Historians still argue whether that moment marked the true beginning of quantum sensing as a practical field or just an elegant curiosity. The researcher gestures to another device on a nearby table, a sleek metal box with a small lens. This one's a magnetometer based on nitrogen vacancy centers in diamond. The defects in the crystal behave like tiny quantum compasses. They can map brain activity or detect mineral deposits miles underground. You crouch, peering into the faint red glow inside the diamond. So, we're using flaws in gems to see the invisible? She smiles. Exactly. Imperfection makes the magic possible. There's a quirky tidbit she throws in with a grin. In one of our early prototypes, someone accidentally used a synthetic engagement diamond. When we ran the scan, it picked up a weird anomaly. Turns out the jeweler had left microscopic metal residue inside. So technically, that ring could have doubled as a quantum magnetometer. You laugh. Finally, an engagement ring that can detect brain waves, she chuckles. Talk about emotional resonance. You walk with her to another section of the lab where sleek black cases line the walls. Inside one, you see what looks like a metal sphere wrapped in wires. That's our cold atom gyroscope, she explains. It measures rotation using the interference patterns of atoms. It can navigate without GPS. You raise an eyebrow. You mean this thing could guide a plane if satellites went down? Or a submarine, she says, or a Mars rover. Quantum sensors don't need external references. They carry their own truth. You like that phrase, carry their own truth. It feels like something much larger than technology, a metaphor for self-reliance written in physics. Historians still argue whether quantum sensing will become the most immediate commercial success of the quantum revolution. Computing is glamorous, communication is political, but sensing is quietly transformative. It's the unseen hand that could redefine medicine, navigation, and earth science before most people even realize it's happening. She leads you toward the back of the room where another team is testing a strange array of antennas. These are quantum radar prototypes, she says. They use entangled photons to detect stealth objects without broadcasting a traceable signal. Your eyes widen. So invisible planes meet invisible detection? She laughs. Exactly. It's like a spy versus spy situation, quantum edition. The air fills with a soft clicking sound as detectors register returning photons. Each click represents a photon pair surviving the trip through a maze of mirrors and filters. Most of them don't make it, she says, but the ones that do tell us more than any classical radar could. You glance at a display showing a fuzzy but unmistakable outline of a drone. The clarity is astonishing. So this works, she nods. In principle, yes. Still early, still fragile. But it's proof that entanglement isn't just spooky, it's practical. The room goes quiet for a moment, save for the ticking detectors. You realize you're surrounded by machines that measure the unmeasurable. Devices that listen to the whispers between particles. It feels strangely intimate, like eavesdropping on the universe's private conversation. There's another display showing time traces from an atomic clock experiment. This one, she says softly, can measure time so precisely it would lose less than a second over the age of the universe. You can't help but whistle. That's overkill. Or perfection, she counters gently, because that level of precision could recalibrate GPS, synchronize the quantum internet, even test theories of relativity at new scales. You find yourself marveling at the irony again. Quantum physics, once blamed for uncertainty, now becoming the foundation for the most precise measurements imaginable. The uncertainty principle, it turns out, doesn't mean chaos, it means sensitivity. The researcher smiles at your expression. Most people think quantum means confusion, But for us, it means clarity. You nod slowly, like sharpening the lens on reality. She grins. Exactly. And the more we listen, the more the universe tells us. The sensors around you hum like a quiet choir. Gravity, magnetism, light, time, all being mapped with impossible grace. You feel something shift inside you, a realization that the quantum revolution isn't confined to labs or algorithms. It's creeping into the very way we see the world. As you head toward the exit, you glance back at the diamond magnetometer glowing softly on its pedestal. Tiny, flawless in its flaws, patiently listening to the heartbeat of atoms. You smile. Quiet side of quantum, you murmur to yourself. Turns out it's louder than I thought. You leave the glowing diamonds behind and step into a smaller, dimmer space that feels more like a late-night cafe than a lab. Soft amber lamps, 2 armchairs, a chalkboard cluttered with half-erased equations and doodles of cats. A handwritten sign taped to the door reads, "Quantum Ethics, enter gently." A researcher looks up from her laptop and smiles. "We keep the lights low," she says. "It helps people admit what actually worries them." You sit, and she slides you a cup of something that smells faintly like chamomile. "You've seen the machines," she continues. "Now let's talk about what they might mean." You glance around the room. A mural on the far wall shows a circuit board fading into a galaxy. Computation dissolving into cosmos. It feels appropriate. "Every technology carries an ethic," she says, settling into the opposite chair. Fire-cooked food and burned cities. Quantum computing. Well, it might rewrite truth itself. You tilt your head. Rewrite truth? She nods. If quantum computers can simulate reality perfectly, they blur the line between discovery and creation. When a model predicts a molecule that's never existed and it works, who's the inventor? The machine, the math, or the universe? You sip the tea, feeling the warmth spread through your hands. "So ethics in the age of uncertainty," you murmur. Exactly. A mainstream historical fact surfaces in your mind. In 2019, the European Union began funding formal studies into quantum ethics, anticipating privacy risks, surveillance implications, and social inequality driven by unequal access to quantum power. Historians still argue whether that foresight was visionary or paranoid, but sitting here, it feels prescient. She gestures to the chalkboard where someone scrawled, "If computation can model consciousness, does it owe empathy?" That was one of our grad students, she says. She wrote it after realizing that quantum machine learning models can generate outputs that look eerily creative. It spooked her. You nod slowly. "Maybe we're building mirrors more than machines." She smiles sadly. "Mirrors that calculate back." There's a pause, then she tells a quirky tidbit that makes you grin. "Did you know a philosopher once tried to write an algorithmic Turing test for ethics? He asked a classical computer to identify morally ambiguous statements. It froze, literally crashed. When he ran it on a quantum simulator, it returned the line, 'Uncertainty is compassion.'" You laugh softly. "That's either profound or broken." "Maybe both," she says. "Quantum systems don't deal in absolutes. Maybe that's what we're missing, an ethics that allows for superposition, for nuance." You let the thought hang in the air. Around you, faint classical music drifts from a speaker, a melody balanced on the edge of melancholy and curiosity. "Privacy is another issue," she continues. "Quantum decryption could expose everything we've ever kept secret. But it could also enforce absolute honesty, communication so secure it can't be faked. What happens to politics when lies become mathematically impossible?" You grimace. "Either utopia or total collapse," she chuckles. "Historians still argue which would come first." She stands and walks to the chalkboard, erasing part of an equation with her sleeve. "Then there's free will. Quantum indeterminacy gave philosophers an excuse to say, maybe we do choose, after all. But if we build deterministic quantum algorithms, does that erase the loophole?" You rest your chin on your hand. "So we might code ourselves out of freedom. Or into a better version of it," she smiles. "Depends on your metaphysics and your funding source." There's something both comforting and unsettling in her calmness. You realize that every revolution eventually reaches this room, the quiet place where power meets conscience. She glances at a sticky note stuck to her laptop. "Remember the humans." "Ethics is the slowest technology," she says softly. "It always lags behind hardware." You think of the corporate labs from earlier, the race for supremacy, the countdown clocks in the security wing. Here, the pace is gentler, but the stakes feel heavier. Maybe ethics is quantum too, you offer. Never one thing until it's observed. She grins. Exactly. Moral superposition. Every choice both right and wrong until consequence collapses it. You both laugh quietly, the sound echoing like a shared secret. She grows thoughtful. There's also the question of access. Quantum computing could widen the gap between the few who can afford it and everyone else. Imagine one company or government holding the keys to unbreakable code, perfect simulation, unlimited prediction. That's not science fiction, it's economics. You picture it, a world divided not by wealth or power, but by computation. Those with quantum processors shaping markets, weather, even policy outcomes. Those without left to guess. It's unsettling. Maybe we'll need quantum democracy, you say. Distributed access to probability itself, she laughs. Now that's a manifesto. On the shelf behind her sits a dusty glass orb containing a single fibre optic strand. Our first entangled photon, she says proudly. We keep it here as a reminder, connection before control. You find yourself staring at it, light refracting through the glass like a miniature aurora. It's funny, you whisper. The smaller the technology gets, the bigger the questions become. Exactly, she says, folding her hands. The universe has always been uncertain. We just finally built something honest enough to admit it. The clock on the wall ticks softly. Outside, night presses against the windows. The conversation lingers, full of pauses that feel as meaningful as words. Before you go, she writes something on the chalkboard and steps aside so you can read it. Progress without reflection is acceleration without direction. You nod, letting the phrase sink in. You should print that on lab doors. We did, she says with a wink. People just walk past faster now. You smile as you stand, finishing your tea. Thank you, you say, for the quiet side of the revolution. She waves you off gently. Remember, every qubit carries a choice. Don't let the hardware decide for you. As you step back into the corridor, the hum of machines feels softer somehow, tempered by thought. You glance once more through the glass at the dimly lit room where uncertainty is compassion and mirrors calculate back. Maybe ethics isn't a constraint on science at all. Maybe it's the only thing that keeps science human. You walk down the corridor again, your steps echoing faintly against the tile floor. The lights grow brighter, more ordinary, and the smell of coffee drifts back in from somewhere down the hall. The next door is propped open, and through it you see rows of desks, a whiteboard covered with neon markers, and a banner pinned to the far wall that reads in cheerful font, Quantum Education Initiative. A young instructor waves you inside. Hey there, she says, come meet tomorrow's quantum workforce. You smile as a dozen students look up from their laptops. Some are teenagers, others mid-career engineers. One woman knits quietly while her simulation runs. On the projector screen glows a cartoon of a qubit as a spinning top labelled Superposition for Beginners. This, the instructor says proudly, is what the future looks like when you start teaching uncertainty in high school. You laugh softly, taking a seat at the back. A student at the front, maybe 17, raises her hand. So, wait. If observing a qubit changes it, does that mean grading homework also changes the answers? The instructor grins. Only if you're a sufficiently entangled teacher. The room erupts in laughter. It feels good, this mix of science and joy. You remember your own days of staring at textbooks full of black and white certainty. Here, the colours vibrate, and the rules feel alive. A mainstream historical fact surfaces in your mind. In 2021, IBM launched Qiskit Global Summer School, an online boot camp that drew more than 5,000 students from 100 countries, all learning to code quantum circuits on real hardware. Historians still argue whether that moment marked the democratization of quantum knowledge or just the beginning of another credential race. But seeing this classroom, it feels like a revolution in slow motion. The instructor gestures toward a sleek grey device on the desk. That's our remote quantum processor interface, she says. Our students can run live experiments on actual machines in New York or Tokyo. They just need a Wi-Fi connection and a lot of caffeine. You raise your eyebrows. So anyone can access a quantum computer now? Pretty much, she says. We even have middle schoolers building entanglement experiments for science fairs. One of them tried to model teleportation using Legos and fishing line. It mostly worked. There's laughter again. Someone passes around a 3D printed block sphere model. You hold it for a moment, feeling the smooth plastic surface beneath your fingers, the axis lines drawn in bright marker. It's like a globe of maybes, you say? Exactly, one student chimes in. Our job's to navigate it without getting lost. Another student points at their screen where a live plot shows interference fringes forming and fading. I'm trying to build an algorithm that can tell when decoherence starts, she explains. Basically teaching my qubit when to panic. You grin. Useful life skill, she laughs. Right? I wish it worked on people too. You glance around the room and realise that this generation will never know a world where quantum computing was mysterious. They're growing up in it, fluent in its weird grammar, comfortable with contradiction. Maybe uncertainty won't scare them, it'll empower them. On the wall hangs a poster with a timeline of computing revolutions. Mechanical, electrical, digital, quantum. Someone has scribbled underneath, next, biological. The handwriting is messy, but the question hangs there like a dare. The instructor walks over to a cabinet and opens it to reveal a small collection of outreach materials. Colourful pamphlets, VR headsets, even a plush toy shaped like a Schrödinger cat. We visit schools, community centres, even retirement homes, she says. Quantum literacy shouldn't be an exclusive club. You nod. Teaching the future to everyone, not just the chosen few. Exactly. There's a quirky tidbit, she adds with a grin. A few years ago, a group of artists in Berlin launched the Quantum Circus. Jugglers, dancers, comedians, all explaining quantum mechanics through performance. They even had a clown playing Heisenberg. You should have seen the uncertainty on his face. You can't help but laugh. I'd buy front row tickets. The students are now running a collaborative exercise, tracing connections between qubits and algorithms on a shared whiteboard. One draws a circuit diagram shaped like a heart. Another labels it Love Gate. You realise they're not afraid of play. They treat complexity like a sandbox, not a wall. Historians still argue whether widespread education will accelerate the quantum revolution or dilute it, turning deep theory into pop science buzzwords. But maybe that's missing the point. Every generation simplifies what it first doesn't understand until it becomes second nature. A student at the back looks up from his screen. You think quantum computing will make jobs disappear, he asks. The instructor pauses. It'll make old jobs transform, she says, just like every tech wave before it. But there'll always be work for curiosity. Curiosity never automates. You jot that down mentally, curiosity never automates. The students nod, thoughtful. One of them mutters, maybe we'll all just become quantum plumbers, fixing leaks in the universe. The instructor laughs. Hey, it's honest work. She points to the large monitor again, now showing a glowing lattice of interconnected nodes. This is what education should feel like, entangled. Knowledge shared across time zones and disciplines. The more we connect, the clearer the picture becomes. You feel a strange optimism stir in you. Maybe the most radical thing about the quantum era isn't the technology, it's the mindset. A willingness to live with paradox, to admit uncertainty, to see potential instead of fear. The class begins to pack up, students chatting about upcoming hackathons and quantum pizza nights. Someone hums quietly. The instructor leans against her desk, looking proud and a little tired. We're raising the first generation that won't flinch at the word superposition, she says softly. They'll grow up expecting reality to be complicated and still love it anyway. You smile. Sounds like hope? She nods. Hope, measured in Planck seconds. As you step out into the hallway again, the laughter from the classroom follows you like a friendly echo. You realise that this is where the future of the quantum revolution truly lives, not just in chilled labs or corporate towers, but in open classrooms filled with curiosity, coffee, and questions that start with what if. You glance back through the glass one last time and see the block sphere model still spinning slowly on a desk, catching the light. A tiny globe of infinite maybes, and you think, the universe has never looked more teachable. The laughter and lightness of the classroom trail behind you, replaced by a low mechanical groan that sounds like an old building breathing. A sign on the next steel door reads, Cryogenics Plant, Authorized Personnel Only. You hesitate a moment, then push it open. A wave of cold air rolls over you, sharp enough to sting your cheeks. Inside, pipes snake along the ceiling like frozen arteries, and every surface gleams with condensation. The hum here isn't gentle. It's the steady roar of pumps forcing helium through narrow tubes. You're back at the roots of the quantum machine, the physical cost of keeping reality still, a technician in a heavy parka spots you. "You here for the tour or the sermon?" he asks over the noise. You grin, whichever's colder. He laughs and gestures you closer to a massive silver tank stamped HE3/HE4 mixing unit. "This," he shouts, "is what separates us from chaos. Every qubit in the building depends on this plumbing. You want superposition? You pay in temperature. You lean toward the pressure gauges. The needles barely move." "How cold?" 13 millikelvin at the bottom plate, he says. "Colder than the cosmic microwave background. Colder than space. We joke that the only thing colder is our funding outlook." You laugh, breath fogging in the air. The joke hides something sobering. Each of these refrigerators gulps electricity by the megawatt and drinks helium that must be refined, captured, and recycled at enormous cost. The miracle of quantum computation runs on a fuel of patience and physics. A mainstream historical fact drifts into focus. When researchers at Oxford first built large dilution refrigerators in the 1950s, they required entire rooms of compressors just to cool a few cubic centimeters of space. Historians still argue whether those early cryogenics engineers were physicists or magicians with wrenches. Either way, every quantum processor today is their descendant. The technician leads you along a catwalk. Below, vats of liquid nitrogen shimmer in pale blue light. "We recover 98% of our helium," he says proudly. "Costs more than champagne per litre." You imagine scientists toasting breakthroughs with cryogenic bubbles. Progress literally on ice. He pauses beside a small digital panel showing an animated diagram of the cooling stages. "Each step down is a fight against entropy," he explains. "We pump out heat from one layer only to dump it into another over and over until the bottom plate is quiet enough for the qubits to breathe." You nod. "So the price of precision is power." "Exactly." He wipes frost from his beard. People talk about quantum computing changing the world, but they forget it already cost the world. Energy, rare isotopes, time. There's a quirky tidbit he shares with a smirk. "One of our prototypes once ran out of helium mid-test because someone left the valve open. We called it the Great Quantum Thaw. Took 2 weeks to get the temperature back." You grin. "Bet that meeting was fun." "Oh, it was heroic finger-pointing." You walk farther, shoes squeaking against the icy floor. The deeper you go, the louder the machinery gets, until it becomes a kind of industrial symphony. Pumps, valves, hiss, and heartbeat. The technician gestures toward a heavy steel door marked Helium Recovery Bay. Inside, transparent tubes carry shimmering gas towards storage tanks. "We run this 24/7, he says. "Helium's scarce. Half the world's supply comes from natural gas fields in the US and Qatar. Lose access. And the quantum boom freezes. Literally." Historians still argue whether helium scarcity will become the first real bottleneck of the quantum age. Some predict new cryogen-free systems using magnetic refrigeration. Others insist nothing beats helium for sheer reliability. For now, everyone keeps stockpiling. You trail a gloved hand along a railing glazed with frost. The cold seeps through the metal, a reminder of how fragile the balance is between progress and depletion. For all our talk of sustainable futures, even the cleanest technology has footprints in hidden places. The technician must read your expression. "Don't look so grim," he says. "Every revolution starts noisy, hungry, and messy. We'll get better. Mini fridges, new materials, room temperature qubits. Someone's already sketching the blueprints." You smile. "So this is the adolescence of the technology." "Exactly. Awkward, expensive, occasionally leaking helium." He gestures you toward a viewing window where you can see a processor suspended inside its gleaming copper shield. Vapor curls lazily upward. Beautiful, isn't it? It is. The whole apparatus gleams like a frozen chandelier, each layer a silent hymn to thermodynamics. You realize that every quantum calculation, the grand simulations, the elegant proofs, rests on this noisy, cold machinery. It's easy to romanticize equations, harder to love compressors. But without them, the math never breathes. There's a note taped near the controls written in black marker. "Keep it cool. Reality depends on it." You chuckle. "Poetic engineers," he grins. "We get artsy at 3 a.m. You stand there for a while, just listening to the rumble. The thought crosses your mind that maybe the real lesson of quantum cryogenics isn't about temperature at all. It's about patience. Every millikelvin earned through years of persistence. Every stable qubit bought by sleepless nights and whirring pumps. You imagine future generations looking back at this era the way we look at steam engines. noisy, inefficient but full of heart. Maybe they'll build quantum chips that hum at room temperature, sipping power instead of guzzling it. And they'll smile at these ancient cathedrals of cold, grateful we were stubborn enough to start somewhere. The technician checks his watch. We're about to start a regeneration cycle, he says. You might want to step back. It gets loud. You do, retreating toward the doorway. The pumps shift pitch, a rising mechanical chorus that fills the room like thunder trapped in a freezer. It's overwhelming, but also oddly reassuring. Humanity, still tinkering with the universe, still trying to keep the impossible stable for just a few more seconds. As you step into the warmer hallway again, the cold clings to your jacket. You glance back through the window one last time. The technician gives a small salute, steam curling around him like breath made visible. You realize he's part of a lineage stretching back to the first firekeepers, guardians of temperature, keeping the extremes in check so that others may build. And somewhere, deep in that humming labyrinth of pipes, the next calculation begins to form, a whisper of logic wrapped in frost. The warmth of the hallway feels almost tropical after the chill of the cryogenic bay, and for a moment you just stand there, thawing, listening to the muted rumble behind the walls. Then you spot another sign, this one simple, black letters on brushed steel. Scaling and integration. You push through the door and step into what feels like the engine room of the entire revolution. Rows of open frames hold circuit boards, cables, and small vacuum chambers. Screens everywhere flash with diagrams of qubit arrays. Grids of glowing dots connected by faint lines, like constellations waiting to be named. An engineer in a hoodie and safety glasses looks up from a cluster of wires and waves you closer. Careful where you step, she says. There's more data underfoot than floor. You look down and notice fiber bundles running like roots across the concrete. The room hums with the sound of 1,000 small fans. This, she explains, is where we wrestle with the impossible problem. How to make 1,000,000 qubits behave like one coherent thought. You nod slowly. Scaling the impossible. Exactly. She points to a display showing a schematic of their latest chip. We've got coherence times up to 300 microseconds now. Sounds good until you realize you need billions of operations to solve anything useful. You study the pattern of connections. Each qubit has its neighbors, its control lines, its readout circuit. The web is so dense it looks more like biological tissue than technology. Reminds me of a brain, you say. She grins. Yeah, except ours forgets everything every half millisecond. You both laugh. A mainstream historical fact flickers in your mind. Since the early 2020s, every major lab, from IBM to Google to startup groups at Delft and USTC, has chased the same holy grail, scalable quantum error-corrected architectures. Historians still argue whether physical qubit count or logical stability is the true measure of progress. The consensus, it depends on who's writing the press release. The engineer taps the display. People think adding qubits is like adding cores in a classical CPU. It's not. Every new qubit multiplies complexity. Crosstalk, noise, timing, drift. Get one line wrong, and the whole thing collapses. Imagine trying to conduct a symphony where every instrument plays a note for 1 millisecond, then explodes. You grin. Sounds like jazz. She laughs. Exactly. Quantum jazz. Improvised coherence. On a nearby bench, another researcher is soldering a dense forest of connections under a microscope. He doesn't look up, just mutters, "If I had a nickel for every time a qubit refused to cooperate, I'd have enough helium for a week." The room bursts into chuckles. You can tell this team lives in equal parts frustration and fascination. The engineer leads you to a glass enclosure housing a new prototype. Sleek, compact, and surprisingly quiet. "That's our modular unit," she says. "Instead of one giant chip, we're building clusters. Small quantum nodes linked by photonic interconnects. Easier to cool, easier to scale." "So like Lego blocks of computation, you ask?" "Exactly. Snap enough together, and you get a supercomputer built from light. It's a gorgeous idea. Modularity not as compromise, but as philosophy. Each node entangled with its neighbors, forming a distributed mind that hums in parallel." She lowers her voice conspiratorially. "Don't tell the investors, but we still lose about 10% of our connections to cosmic rays." You blink. "Cosmic rays?" "Yeah. Space keeps photobombing our experiments." You laugh. "So the universe itself is your biggest troll?" "Always has been." She hands you a pair of safety glasses. "Here, look at this." You peer through the viewing window as a test run begins. Tiny pulses of light flicker across the qubit grid, tracing patterns that shift faster than your eyes can follow. The machine hums in response, a faint chorus of digital chirps that sound almost alive. That's a calibration sequence, she says. Each pulse corrects phase errors between qubits. We run it millions of times a day. You ask the obvious question. What happens if you stop? She smiles wearily. Reality stops agreeing with us. You think about that, the sheer fragility of it. An empire of computation sustained by continuous tuning. A digital violin string that must never stop vibrating. There's a quirky tidbit she shares as the system cools back down. We once had a grad student who claimed he could hear the difference between good and bad calibration runs just by the tone of the pumps. He called it listening to decoherence, and he was right. You grin. Quantum audiophile. Exactly. We still make him do diagnostics by ear. The display flashes green, test complete. That's one cluster stable for 20 seconds, she says proudly. A new record. You nod, impressed. Doesn't sound long. It's an eternity in quantum time. The lab breaks into scattered applause, tired smiles everywhere. You sense how much of their work is measured not in years or budgets, but microseconds of success. Historians still argue whether scaling will come from brute force engineering or some elegant new physics. Topological qubits, Majorana modes, maybe room temperature spin systems. But in this moment, the theory doesn't matter. Progress is measured by a single stubborn fact. They made the noise quiet, even if only for a breath. You look around the room again. Every table, every screen hums with purpose. The people here aren't just building machines, they're building endurance, systems that can survive their own fragility long enough to matter. The engineer wipes her hands and leans on the table. Sometimes I think of it like gardening, she says. We plant coherence, prune noise, water the circuits, and hope the universe doesn't step on the flower bed. You smile. That's the most poetic description of debugging I've ever heard. She chuckles. It's also the most accurate. The lights dim slightly as the next test prepares. For a moment, all you hear is the faint hum of cooling fans like distant wind through trees. The engineer glances at the display one more time and says softly, "We'll get there. Maybe not today, maybe not us, but someone will." You nod, feeling the weight and hope in her words. Scaling the impossible isn't about conquering nature, it's about coaxing it into cooperation, one qubit at a time. As you step toward the exit, you glance back at the prototype still glowing under the glass. It reminds you of a constellation, an unfinished sky waiting for names. The future, it seems, is being assembled one flicker of coherence at a time, fragile and fierce. And somewhere inside that luminous grid, the first outlines of tomorrow's machine are already learning to hold still. The next corridor feels different, less sterile, more human. The walls are plastered with movie posters, vintage comics, and memes about cats both alive and not. You follow the muffled sound of laughter until you reach a room that looks like a cross between a break lounge and a fan convention. A neon sign over the door blinks, Quantum Culture and Mythology. A researcher in a faded Marvel t-shirt glances up from a couch piled with papers. "Ah, you found the fun lab," he says, grinning. "We study how the world imagines quantum stuff. Spoiler alert, half of it's wrong, the other half is just poetic enough to make us jealous." You step inside. The walls are covered with clippings, magazine covers screaming "Quantum Leap in AI," movie stills of glowing portals, newspaper headlines predicting everything from immortality to apocalypse. "We keep them," he says, "for anthropological reasons, and for morale." You chuckle. "So you're archivists of hype?" Exactly. A mainstream historical fact floats into memory. The phrase "quantum leap" actually originated in 1927 to describe the smallest possible jump an electron could make between energy levels. Historians still argue whether popular culture's use of it, to mean sudden, dramatic progress, was an accident or an act of poetic irony. In physics, a quantum leap is the tiniest change possible. In Hollywood, it's the biggest. The researcher gestures to a poster of Avengers, Endgame, where Tony Stark brandishes a glowing device labelled Quantum Tunnel. "People think of quantum as magic," he says. "It's our generation's alchemy, mysterious, powerful, vaguely dangerous." You grin. "And marketable." "Very." There's a quirky tidbit he shares with a mischievous smile. Back in the early 2000s, an actual self-help movement called quantum healing claimed consciousness could manipulate subatomic particles to cure disease. It sold millions of books. My mum still swears by it. You laugh. So quantum mysticism pays better than grant writing. Always has. He leads you to a display table piled with gadgets, quantum-branded watches, skincare products, even an energy drink called Qboost. None of this has any real physics in it, he says, but it tells us something about how people crave mystery. Quantum became shorthand for anything too complicated to explain, but too cool to ignore. You pick up a glittery perfume bottle labelled entanglement. Smells like correlation. He grins. Probably like wishful thinking. In the corner, another researcher scrolls through social media posts filled with phrases like quantum manifestation and timeline shifting. We track misinformation too, she explains. Once quantum theory left the lab, it mutated into metaphor. Everyone wants a piece of the uncertainty. You can't help but admire it. The way an esoteric branch of physics became pop culture currency. The quantum world has inspired more novels, movies, and conspiracy theories than most scientists dare to admit. From Interstellar's tesseracts to Ant-Man's subatomic world, it's the mythos of modern times, an invisible realm that explains everything and nothing. Historians still argue whether the media's exaggerations helped or hurt public understanding. Some say hype brought attention and funding, others say it buried real science under glitter. The truth, as always, sits in superposition, funded but misunderstood. The researcher throws up his hands. Look, we can't be mad. The confusion is part of the charm. People are trying to wrap art around uncertainty. That's culture doing what it does best. He shows you a small display case labelled Quantum in Art. Inside are holographic prints of abstract shapes that shift as you move. Paintings that literally change perspective with observation. Artists got there before engineers did, he says proudly. They understood that the observer changes the observed long before we built the math. You wander toward a whiteboard where someone has written a mock movie pitch. Quantum hearts, 2 entangled lovers, 1 collapsing wave function. Beneath it, someone else scrawled, rated PG-13 for superposition. You laugh so hard you nearly drop your notebook. He nods. That's what we do in here. Decode the mythology, find humour in it. Because if you don't laugh, you'll spend your life explaining that quantum computers don't actually travel through time. You raise an eyebrow. You mean they don't? He sighs dramatically. If only. We'd never be late for conferences. A third researcher chimes in from across the room. The funny part is, pop culture occasionally gets it right by accident. Like entanglement is instant correlation, and quantum tunneling does mean particles can pass through barriers, but combine those in a movie script and suddenly everyone thinks we're building teleporters. You nod. It's poetic compression, too good a metaphor to let accuracy ruin it. He grins. Exactly. The dream version of physics. You glance at a glass case in the corner holding an original script of the 1980s TV show Quantum Leap. We use that title in outreach events, the researcher says. When we tell people the real meaning of Quantum Leap, they get this look, like we just told them Santa Claus is a wave function. You laugh again, and for a moment the room feels almost like a comedy club for physicists, where jokes about decoherence get applause instead of confusion. Then one of the younger researchers, scrolling through her phone, looks up thoughtfully. You know, she says, maybe it's good that people romanticize quantum stuff. It keeps curiosity alive. Mysticism fades, but wonder sticks around. Everyone nods quietly. Even in the laughter, there's truth. Humanity's oldest instinct isn't to calculate, it's to imagine. Historians still argue whether culture drives science or the other way around. But standing here, surrounded by memes, movie props, and philosophers in hoodies, you realize it doesn't matter. Every story we tell about the quantum world, accurate or not, is a reflection of the same yearning, to touch the invisible. You turn toward the door, but before leaving you spot a poster that sums up the spirit of the room. It shows Schrödinger's cat lounging on a couch with sunglasses captioned, "Still both dead and fabulous." You chuckle, shaking your head. You people are incorrigible. The researcher waves. Someone's got to keep the mystery fun. As you step back into the corridor, the laughter fades, replaced once more by the steady hum of machines. You can't help smiling. Maybe science and storytelling aren't opposites after all, just different dialects of the same language. And somewhere between fact and fiction, uncertainty and imagination, the quantum revolution keeps spinning. Part physics, part folklore, entirely human. You walk through a final glass door expecting more humming machines, but instead you find quiet. The lab corridor has opened into a wide, open observatory-style space. The ceiling arcs above you in matte silver. The floor a polished mirror that reflects your every movement in soft focus. At the far end of the room, a single quantum processor sits under a halo of light, its gold wiring gleaming like a sun suspended upside down. The plaque beside it reads Threshold Prototype Theory Realized. You take a slow breath. This is it, the place where all the threads converge. The frozen cathedrals, the dancing qubits, the corporate races, the ethical debates, the memes. It all led here, to a machine that no longer asks if quantum computing can work. It simply does. A researcher stands nearby, hands tucked into his coat pockets, gazing at the machine like an old friend. "You made it to the end," he says softly. "Not many tours go this far." You smile. "I figured if I was going to understand quantum reality, I might as well see where it stops being theory." He nods. "Funny thing is, it doesn't stop. It just gets quieter." You approach the processor. It's beautiful. An intricate spiral of copper, gold, and sapphire that seems to hum even without motion. The air here feels heavy with possibility. "This one," the researcher says, "is the first system we've built where every component, hardware, software, communication, is quantum native. No classical bottlenecks, every operation entangled from end to end." You blink. "So it's self-contained? Fully quantum?" "Exactly. It doesn't need translation anymore. It speaks the universe's language fluently." That phrase lingers in the air. Speaks the universe's language. You feel a strange shiver, the kind that comes when awe and unease blur together. A mainstream historical fact surfaces. Something about the first transistor in 1947, when a small hunk of germanium changed the world. Historians still argue whether that invention birthed the digital age or merely revealed it was already inevitable. You suspect the same debates will haunt this machine too. You ask the question hanging between you, what happens now? He smiles faintly. Now we stop proving it works. We start asking what it means. You glance around the room. There's no bustle, no technicians frantically recalibrating. The hum is low and steady. For the first time, the technology feels serene. "You're standing," he says, "at the line between theory and reality. Everything beyond this point runs on laws we used to call impossible." You let that settle. "So we've crossed it," he nods. "We crossed it years ago. We just hadn't noticed until the noise quieted down." He steps forward and touches the edge of the processor's casing. "It's funny," he says. "This machine still follows the same principles as the first quantum prototypes. Superposition, entanglement, interference. But now we can scale it, trust it, program it like any classical system. Except it doesn't think linearly. It thinks in clouds." You raise an eyebrow. "Clouds?" He smiles. "Probability clouds. It doesn't move from problem to solution. It collapses them together. It doesn't decide. It resolves." You look at the soft reflections on the mirrored floor. And humans? Where do we fit once the machines can resolve everything faster than we can imagine? He chuckles gently. "The same place we always have, asking better questions." There's a pause. The hum of the machine deepens for a moment like an exhale. Somewhere deep inside, 1,000,000 qubits flicker in and out of existence, performing calculations that no classical brain could follow. You can almost feel it, the flow of information, the probabilistic heartbeat of a new era. He gestures toward a large screen on the wall. It displays a simple message. Computation complete. Confidence, 99.999999%. "What did it solve, Weiss?" you ask. He shrugs. "Doesn't matter, really." The answer was less important than proving we can now trust it. You smile, shaking your head. "The universe's most expensive demonstration of trust." "Pretty much." He walks toward a control console and taps a key. The chandelier of circuits glows brighter for a few seconds, then fades to a faint amber. "We've reached the point," he says, "where quantum technology is no longer fragile. It's infrastructure. Someday soon, people won't even realize they're using it, just like no one thinks about transistors anymore. You imagine it, a world quietly humming with invisible coherence, quantum encryption securing every message, quantum chemistry designing every material, quantum AI optimizing entire ecosystems. Historians still argue whether humanity ever truly understands its own revolutions while they're happening. You suspect we don't. We just live inside them until they feel normal. The researcher folds his arms, watching the faintly glowing machine. "You know," he says, "I sometimes miss the chaos, the leaks, the noise, the guesswork. But I also love this part, the stillness, the proof that theory can eventually become reality." He glances over at you. "And you?" You look around the room, at the reflections, the symmetry, the calm. "I think," you say softly, "that we've built the closest thing to magic the universe will ever allow." He smiles. "And it still obeys physics. That's the trick." You laugh quietly. "So what do you call this stage? Supremacy? Advantage? Maturity?" He shakes his head. "None of those. We just call it balance." The word lingers as you take one last look at the golden lattice. It hums like a living organism, its rhythm almost familiar now, the sound of equilibrium between chaos and order, between dream and data. You realize you're no longer peering into the future, you're standing inside it, and in that still, cold air, surrounded by the quiet machinery of impossibility made practical, you whisper the only phrase that fits. Theory has finally caught up with itself. The researcher hears you and nods. Welcome to reality. The lights dim slowly, the hum fades, and for a heartbeat you swear you can feel the Qubits exhale. A sigh of completion, or maybe just the beginning of something larger. The room settles into silence, and your breathing slows with it. The cold air softens, the sharp lines of machinery blur into gentle reflections, and for the first time all night, nothing moves. The hum you've been following through labs and laughter and impossible experiments becomes almost a lullaby now, steady and low, like the pulse of a sleeping world. You take one last step back, the mirrored floor catching faint ripples of light from the processor. Somewhere deep inside, qubits continue their quiet oscillations, a rhythm older than math, as natural as the heartbeat of stars. The researcher is gone. The only sound left is the faint whisper of helium and time. You realize that all the noise, the panic about security, the races for supremacy, the philosophical questions, has folded neatly into this calm. This is what crossing the line between theory and reality sounds like. Not thunder, but breathing. Outside, the night waits. Ordinary, uncollapsed. You step through the door and feel the warmth return to your skin. The world hasn't changed shape, yet everything inside it has shifted slightly, like sand settling after the tide. You pause, watching your reflection in the glass one last time, a human silhouette framed by the glow of a machine that finally learned how to whisper back. The air feels softer now, the edges rounded. Maybe that's the quiet gift of quantum thinking. That uncertainty, when accepted, becomes serenity. You smile to yourself, exhale slowly, and let the hum fade into the distance. The journey ends not with a calculation, but with calm. Sleep well. The universe will keep computing while you rest.